Okay, well, I think we will get started. Can everybody hear me okay?
Yeah.
Yes.
Okay, okay, wonderful. Thank you. Well, hello, everybody, and welcome to the 2021 awards ceremony of the ARO Midwinter Meeting. My name is Ruth Latupsky, and I'm just wrapping up my term as president with John Ogalai taking over. It has been a remarkable year, and I'm delighted that all of you are here today to celebrate the achievements of our colleagues. ARO is a truly remarkable organization for so many reasons, and one of them being that we love to celebrate the success of our colleagues and mentors. For many years, the Award of Merit was the singular award given at our meeting, and some years ago, we then added the Young Investigator Award to acknowledge and celebrate the work of the younger scientists in our field. And if you look at the list of those young investigators on our website, you see that many of them have gone on to become leaders in our field. We have also recently realized that in addition to these two awards, there are so many other important ways that we want to celebrate our colleagues and their successes. So this year we have two new awards that we are delighted to inaugurate, the Pioneer and the Innovator Awards. For each of the awards that we will hear about today, numerous strong and wonderful nominations were brought forth, and the awards committee had a really tough job. They spent a lot of time reading the nominations carefully and making very tough choices in their selection process. So I really want to thank the awards committee for their hard work and to thank the people who took the time to write such thoughtful and comprehensive letters. The way that the award ceremony today will work virtually is that each nominee will be presented to us by their nominator or nominators, who will say a few words, either live or pre-recorded, about the research, trajectory, and contributions and career and incredible work that brought them to us today in this way. We will then hear from the award recipients, again, either live or pre-recorded, and each of them has either already received or will be receiving their award certificates in the mail. But I have photos of the award certificates to show you in the PowerPoint presentation. So relax and enjoy the most wonderful few hours in which we celebrate our award recipients today. And before I do that, I want to call out the Poster Blitz winners. So we have divided those into two categories, the student winners and the postdoc winners. And there are 3 in each category. And the first place winners are going to receive a small gift card or a Visa card with cash card to thank them and to appreciate them. And I also want to thank everyone who gave the Poster Blitz presentations. You did a really terrific job, and the Poster Blitz committee for all their hard work as well. So our Geraldine Fox Young Investigator Award this year goes to Donatella Contini from the Department of Anatomy and Cell Biology at University of Illinois College of Medicine. I loved calling you on the phone and telling you about the award. It was one of the nicest phone calls. And this award is for pioneering investigations of synaptic transmission in the vestibular system. Congratulations, Donatella. It's such a pleasure to, I wish I could give you this in person up on the stage, but here we are. And we will be... So I'm going to hand this off now to Jonathan, Art, and Gay Holstein, who are going to present and talk about you.
Thank you, Ruth, and good day, morning, or afternoon to you all. 70 years ago, Sir Bernard Katz and colleagues reported the first direct measurements of the end plate potential and divined that it resulted from the action of acetylcholine on the muscle membrane. They also described small spontaneous depolarizations of the postsynaptic membrane potential that occurred even when the motor neuron was not stimulated. The existence of these miniature potentials was used to argue that neurotransmitters in presynaptic terminals are released in discrete packets or quanta with effective durations of a millisecond or two.
Hair cells share with photoreceptors the ribbon synapse, which is correlated with high rates of quantal transmission that reflect graded potentials in the receptors. A prior recipient of the Young Investigator Award, Elizabeth Glowatsky, was the first to demonstrate with Paul Fuchs that can characterize the quanta released from auditory inner hair cells in 2002, and this opened the door to the exploration of the synapse.
In the auditory and vestibular systems, there are morphological specializations such as end bulbs and calyceal endings, where pre or postsynaptic cells may envelop their synaptic partners. Determining the functional significance of these extensive synaptic clefts has remained experimentally challenging.
In a pandemic year, with talks of viruses and vaccines, it's appropriate to recall the words of the immunologist Sir Peter Medawar. In his book, Advice to Young Scientists, he admonished all of us, regardless of age, to choose important questions. For those of us interested in synaptic physiology, it is the multiple modes of transmission and the large apposition between cells in the vestibular system that make these structures so attractive for study. This year's recipient of the award began her studies at the University of Pavia, a home institution of both Alfonso Giacomo Corti and Antonio Scarpa. Dr. Contini is technically gifted with an aptitude and passion for science. She fearlessly pursues approaches that produce clean and interpretable results, even when the technical developments are difficult and time-consuming. She has a remarkable ability to observe with a well-developed sensitivity to the data and what it may convey. This has allowed her to create truly novel and testable hypotheses.
In this, she shares many of the attributes of the person for whom this award is named. Jerry Fox has been a passionate supporter of research on the inner ear, contributing substantively to the Deafness Research Foundation, advocating for the establishment of NIDCD, and ultimately serving as the chair of the NIDCD Advisory Board. She founded the National Organization for Hearing Research in order to encourage, as she said, young researchers with fresh new ideas. John and I believe that Donatella Contini epitomizes the generosity, creativity, energy, brilliance, and enthusiasm for new scientific thinking and research that Ms. Fox advocates for with such dedication and tenacity. Donatella.
Okay, thank you so much, Gay and John, for your beautiful introduction. I'm very honored to receive this award. In the vestibular system, from the biophysics of hair cell and afferent ion channels, it wasn't obvious how quantal transmission could take place. Shown in red are the afferents that synapses on the base of hair cell. There are two categories of hair cell defined by their synaptic types. They are defined in terms of their contact with the afferents. Type 1 hair cell is surrounded by a calyx. Type 2 hair cell either have a button ending or synapse on the outside of the calyx. The synaptic cleft between type 1 hair cell and calyx is an extensive volume where ions and transmitter may accumulate. Let's look at the different modes of transmission that result from this extensive cleft. I will start with quantal transmission. These are single electrode recording from the afferents. Here at -68, the afferents showed single EPSPs. Sometimes they appear to some. When the calyx is depolarized at -63, action potential are triggered from the Tolles event. So a fundamental question would be how the two cells achieve the potential necessary for synaptic transmission and the firing of action potentials. The approach we developed to answer this is shown here. We recorded simultaneously from type 1 hair cell and calyx. The calyx was held constant at current fixed. Instead, we injected different currents to her cell, or the her cell was stepped at different potential. These experiments are the two electrode extension of the single electrode work I did at Pavia for my dissertation, and that was done concurrently at Newcastle from Rebecca Lim and Alan Brichta. Okay, here on the left, injecting currents in type 1 hair cell, their cell show this transient peak followed by a lower plateau. In contrast, the calyx has this exponential recovery function. In voltage clamp holding both hair cell and calyx at -100, we see the polarizing hair cell. The cell generate outer potassium currents, and these currents are associated with generation of inward current in the calyx. Such inward current in the afferent is more or consistent with something accumulating in the cleft. When I started, one likely candidate for accumulation was potassium, as suggested by Chen, a student of ETOC at Rochester, based on the work by Frank Noser and Hodgkin. We use the hair cell responses in voltage clamp to estimate the potassium concentration in the cleft. This concentration was elevated whenever the cell or the afferent was depolarized. Unexpectedly, during these studies, we also found elevated potassium increases their cell and afferent conductances facing the cleft. These conductances allow the transduction current to flow out of the hair cell, across the cleft, and into the postsynaptic afferent. The dynamics of electrical coupling due to these potassium sensitive conductances can be shown by holding the cell at different potential. Here at -100. The hair cell has this sigmoidal increase in the outer current. In parallel, the calyx has this sigmoidal increase in the inward current. Near the resting potential at -70, the situation is different. There will be a steady flow of potassium out of the hair cell and into the cleft. At the top, here we can see at -70, there is a large instantaneous jump in the cell, followed by an increase to a new level. This jump in the cell is associated with a smaller jump here in the calyx, in the inward current. So since it is hard to see at this scale, to make the difference clear, I have replotted the afferent responses at larger magnification. Here, again, -100 sigmoidal rise. At -70, we see up on the laser pointer this small 25 picoamps of jump current. This represents 2% of the outer hair cell current. The percentage of coupling varies from case to case, but it is always as large as that between cone photoreceptors in the retina. It varies from 350 picosiemens to 2.5 nanosiemens. Summarizing, elevation of the potassium in the cleft has 3 effects on synaptic transmission. First, depolarize the hair cell, allowing calcium influx and vesicle fusion and quanta transmission through postsynaptic AMPA receptor. Second, it depolarizes the afferent to potentials where single quanta may be large enough to initiate action potentials. Third, high potassium in the cleft increases the conductances facing both cells. This opens a route of intercellular coupling that relies on ion channel conductances rather than gap junction. I would like the scientists who helped me a lot. On the left is the Pavia group who were responsible for my early professional development. On the right, Chris Holt, who taught me the turtle preparation and demonstrated the professional generosity that I try to emulate. Jay Goldberg, who brought me to Chicago, I'm so sorry, I've got emotional, and center stage to my wonderful collaborators, Gay Holstein and Jora. Gay has taught me to think about interplay between structure and function, while John has influenced me essentially everything, technically, intellectually, and professionally. So, John, thank you so much for everything you have done for me. Lastly, I thank the Award Committee and Mr. Gerald D. Fox for giving me this tremendous honor. I'm truly grateful for it.
That was a beautiful, beautiful presentation. Thank you so much. And Donatella Contini for the 2021 Young Investigator Award. And that was a really beautiful presentation.
Thank you so much. I'm sorry.
No, this is beautiful. And I would be emotional too. Absolutely. So it is now my honor to introduce the Award of Merit recipient, Tom Yin, who's receiving the award for Foundational Experimental Paradigms and Studies of the Physiology, Behavior, and Anatomy of Spatial Hearing. This award was by committee from a number of folks who worked and studied with Tom, and I wanted to also say that it's especially meaningful to me because I got to train with Tom in the early 1990s, and working in his lab was the most incredible experience. So I'm going to now hand this off to Dan Tolan, who I think pre-recorded a really beautiful tribute.
Welcome everybody from around the world. Thank you for attending this event. Today we gathered to honor Tom Yin from the University of Wisconsin as the recipient of the 2021 Association for Research in Otolaryngology Award of Merit. Per the ARO guidelines, the ARO Award of Merit recognizes an individual who has made substantial scientific advancements and contributions to the fields encompassed by otolaryngology. Tom was awarded this honor for, as it says down there, for foundational experimental paradigms and studies of the physiology, anatomy, and behavior of spatial hearing. My name is Dan Tolan, professor at the University of Colorado. I was a postdoc with Tom in the late 90s and early 2000s. I'd like to briefly thank the nominating group. You can see their names and affiliations here. The nominating group did a great job helping put together this roasted toast. First, a little bit about Tom and his background. Where did Tom come from? Tom was born in Kunming, China, where his parents had fled to escape the Japanese invasion of northern China before World War II. In 1948, here's a picture of Tom with his mother before immigrating to the US. Get little Tommy there. The Yin family then immigrated to Denver, Colorado in 1948, where Tom's parents were graduate students. But when the communists defeated the nationalists in China in 1949, the family decided not to return to China, instead stay in the United States. Tom attended schools in the Denver area. Here's Tom's high school graduation photo. And then he went on to Princeton University. Here's a picture of Tom and his family, 1954, so a few years after coming to the United States. Tom's two brothers are also shown here, Frank and Jerry. Both of them are also world-renowned academics in their respective fields, similar to Tom. As mentioned, Tom went to Princeton University, majored in electrical engineering, and apparently Tom was a bit of a prankster. Here's a picture of Tom on the cover of the student newspaper, where apparently Tom and a buddy there had just stolen the bell ringer in one of the main towers on campus. This is apparently an annual tradition at the start of the semester. So nice work, Tom. He still has it to this day as well. Tom then went to graduate school at the University of Michigan. Interesting story here. He went to, again, major in electrical engineering, but after a semester or two in Ann Arbor, he discovered that practically all the research in electrical engineering at that time was war-related and sponsored by the Department of Defense. And so not wanting to support directly the war effort, he decided to complete course requirements for a master's degree and then join the Peace Corps. And just before he was supposed to go to the Peace Corps for training, by chance in the hallway, he met Professor William J. Williams and had an interesting conversation. Professor Williams told Tom that his research in his lab was funded by the National Institutes of Health and not the Department of Defense. And Tom asked, basically, that sounds great, but what do you do in your lab? And Professor Williams replied, bioengineering. And Tom at that time had no idea what that was. And he said, cool, yeah, but what's that? What's bioengineering? At that pivotal moment, Tom put his Peace Corps plans on hold and decided to explore this new field of bioengineering. In the Williams lab, Tom applied engineering techniques and analyses to study brain circuits and behavioral function. Tom's PhD work focused on the transfer characteristics of neurons in the thalamus relaying information about joint angles. At the time, the classic work in this kind of neuroscientific work was being done by Vernon Mountcastle at Johns Hopkins University. So when Tom defended his dissertation, got his PhD, arranged to do a postdoc in the lab of Vernon Mountcastle at Johns Hopkins. While waiting for his NIH postdoctoral fellowship to start, Tom had the opportunity to spend 6 months doing a postdoc with Sir John Eccles, Nobel laureate John Eccles, at SUNY Buffalo in upstate New York. And Tom worked on an electroanatomy experiment studying cerebral inputs to the cerebellum, right? So learned a lot about motor circuit function. And this proved to be surprisingly fortuitous when Tom started looking for faculty positions after his postdoc. I'll come back to that. Tom's postdoc work with Vernon Mountcastle at Johns Hopkins was also sort of a pivotal experience in Tom's academic career. Tom's postdoc work studied visual motor properties of neurons in the posterior parietal cortex of awake behaving primates, which of course underscores the interest in behavior that grounded Tom for basically the rest of his scientific career. Here's one paper that Tom published with Vernon Mountcastle in the journal Science. Here Tom showed that in awake behaving primates, I won't go through the details, but basically neurons in parietal area 7B are involved in directing visual spatial attention necessary for accurate eye movements, or saccades. Key to this finding was the simultaneous recording of both neuron responses in awake animals and also eye position as an indicator of the animal's perception. And we'll see this technique that Tom will use again in studying the neural correlates of spatial behavior 20 years from this point in the future in Tom's auditory work. In 1997, Tom was recruited to join the Department of Neurophysiology at the University of Wisconsin with requirements to teach motor systems. And of course, he had this skill set based upon the postdoctoral work that he had done, largely with John Eccles in SUNY Buffalo. It turns out teaching is one of Tom's passion. Anybody that knows Tom knows he's a dedicated teacher, does way above and beyond the amount and scope of teaching required at kind of the level of science that Tom does. And Tom is such a dedicated teacher that in 2003, he was awarded the Chancellor's Distinguished Teaching Award at the University of Wisconsin. This award is given to one faculty member on the entire campus, which is a large campus. So this is a great testament to Tom's teaching dedication and of course also skills that the students love him. Now on to a little bit about Tom's science in the auditory system and why we think he's deserving of the ARO Award of Merit. While waiting for his NIH grant at University of Wisconsin, right, Tom's a new faculty here in the mid-70s. He got an NIH grant to study motor function, kind of based upon his postdoctoral work. But Tom ran into this guy, Shig Kawada. Sadly, Shig passed in the last year or so. But Shig, as many of you know, is also a world-renowned auditory neurophysiologist. And this fortuitous meeting of two great minds boded well for sort of the history of Tom's research and basically the first start. Tom had never done work in the auditory system before being teamed up with Shig. At this time, Shig Kawada was a postdoc with Jersey Rose, studying the binaural response properties of cells in the inferior colliculus in the auditory midbrain. And according to neuroscience mythology or lore, Jersey Rose told Tom and Shig that there were so-called gold in their hills. And by hills, Jersey Rose was referring to kind of the mounds that form the inferior colliculus, also is in terms of gold, referring to the ability of some neurons in that structure to encode the interval time difference cue to sound source localization. This fortuitous pairing was very productive and started a career-changing interest for both Tom and Shig, and of course, a lifelong friendship and collaboration. Tom and Shig published in a pretty short period of time, just a couple of years, something like 7 or 8 seminal papers on the coding of interval time differences in the auditory midbrain. Now, while Tom continued his visual motor work, right, his NIH grant was funded, he was doing studies on visual motor responses. The lure of those fascinating cells that were sensitive to microsecond time differences in the input to the 2 ears was irresistible and kept drawing Tom back to the auditory system. And a key guide to Tom's studies was the publication of a paper some 30 years before Tom and Shig started to look at this problem, entitled "A Place Theory of Sound Localization" by, of course, Lloyd Jeffress. And Jeffress postulated that the brain encoded the timing differences of sounds at the 2 ears, relying on 3 different circuit functions. And the first of these circuit functions was phase locking of action potentials to ongoing sounds by the auditory nerve fibers. The second component was some mechanism to create delay lines. So you can see there's differential physical delays into the central neurons. And finally, that there are central comparator neurons that act as coincidence detectors of simultaneously arriving action potentials from the 2 sides. Now, fascinatingly, Tom, coming from an engineering background, tackled every single one of these 3 sort of legs of the stool, if you will, over 40 years. He tackled the problem of phase locking by afferents using in vivo physiology and modern stimulus delivery and design in the auditory nerve, in the cochlear nucleus bushy cells, where one of the things that Tom in his lab demonstrated was that the phase locking in the cochlear nucleus is actually significantly enhanced relative to that in the auditory nerve. And then also, of course, they studied the medial nucleus of the trapezoid body, which also showed enhanced phase locking similar to the bushy cells. Second, Tom used modern neuroanatomical methods to look at delay lines, anatomical studies of the afferents to the medial superior and also the lateral superior. And finally, the mechanism of coincidence detection. Tom used in vivo physiology and also computational modeling and applied those studies to the inferior colliculus, most notably this medial superior lobe, where we think something like the Jeffress model is actually implemented. And Tom also looked at the lateral superior lobe and the superior colliculus. So based just on that body of work, the ARO Award of Merit would be fitting for Tom Yin. But wait, there's more. Tom always, harkening back to his PhD and postdoctoral days, thinking about how behavior and physiology combine. In the mid-90s, Tom's lab began to leverage the methods from his postdoc to study sound localization behavior. Of course, just like his postdoc work, this required simultaneous measurement and recording of neural responses. So here you see the animal preparation fitted with electrodes, and of course also monitoring the positions of the eye, head, and also the external ears. Okay. Over the next 20 years or so, Tom's studies, along with his colleagues, dove into a wide variety of different auditory spatial phenomena in the underlying neurophysiological mechanism. I highlight just here a couple of them, examining multimodal sensory integration in the superior colliculus, the role of the auditory brainstem in the so-called precedence effect, the role of spectral cues for vertical sound localization, spectral temporal and level duration effects in sound localization, and the relative versus absolute sound localization. So that's a sense that, in a nutshell. Tom will talk more about some of this, of course, in the lecture that follows this. So enough about Tom's vast scientific accomplishments. A few interesting things. Tom is an avid outdoorsman. He loves everything outdoorsy. Here's a few pictures of Tom fishing at the Auditory Brainstem Dude Ranch meeting that Tom loved to go to every other year. A little joke here. So here's Tom in this middle picture saying, back in the day, auditory brainstem neurons, were like this. They were huge, easy to find and study. And here's me, when I'm a postdoc in the lab, like, really, this is it. This is all I can find, right? They're not that big. Again, all things outdoors. Tom was an avid outdoorsman. And of course, first and foremost to Tom, as anybody has spent time with Tom, is of course his family. His wife Lil of 48 years, his 2 children, Laura and Eric, and Tom has 3 grandchildren. Spends tons of time, teaching them how to fish, reading, camping, doing fantastic stuff. Before I conclude and commence a toast to Tom on the award of the ARO Award of Merit, I'd just like to briefly point out the lengthy list of wonderful people that have worked with Tom over the years. We were fortunate enough a few years ago to host a Festschrift for Tom in 2015, inviting people from all around the world that could come. It was a great event. One of the cool things I thought about this event was that instead of Tom, having us old people get up and give talks about, how they had a great time working with Tom, Tom actually wanted his sort of academic grandchildren to give the talk. So the kind of featured events featured talks and seminars by basically the students and postdocs that are in the labs of the people that Tom worked with. So a pretty special event. Here's actually a list of some of the people. I'll leave this up for a couple of seconds so that you can see the wonderful, fantastic people that worked with Tom over his career. So with that, wherever you are in the world, no matter the time, please raise a glass or whatever you happen to have to congratulate Tom Yin for the ARO 2021 Award of Merit. Congrats, Tom.
Thank you, Dan. That was so beautiful. And I know that many of us around the world would love to be able to give Tom a hug, shake his hand, and celebrate in person. And I definitely feel that way. That was really beautiful. And I see that Lil is here and some members of Tom's family. So this is really absolutely wonderful to be here virtually together. And here's Tom's talk now.
Thank you, Dan, for that generous introduction. I'm deeply honored and delighted to receive the AR Award of Merit. I'd like to thank the Society for this distinction and hope that I can reach the high bar set for this lecture by previous winners. It
listens for the tiny sounds of its prey moving about below, but must take great care not to scare them away.
This short video illustrates one of the premier examples of sound localization ability. I wish that I could say that I will be showing you behavioral data using this animal model. In Wisconsin, we have foxes and plenty of snow and rodents, but the behavior I'll show you is much less exciting. So here's an outline of the talk. I will begin with a brief review of the pertinent properties of auditory nerve fibers, and then review the cell types in the coca nucleus and superior olive that are thought to be important for this task. Then I'll spend most of my time on the physiological and behavioral studies from my lab aimed at understanding this intriguing ability. Since all of the information needed for neurocomputation of acoustic space must be contained in the auditory nerve, it makes sense to start there. So auditory nerve fibers have two important properties illustrated in the slide. They are sharply tuned in frequency with different CFs. Here we show frequency tuning curves of many auditory nerve fibers. CFs depend on the location of the inner hair cell that the auditory nerve fiber innervates along the base to apical extent of the cochlea. And in B, the responses to a pure tone burst at CF, auditory nerve fibers show a stereotypical response with either rapid or slow adaptation. For low, but not for high frequency auditory nerve fibers, there is phase locking, which is a response to each cycle of the sinusoidal tone, as shown below. This is seen more clearly in the next slide. So not surprisingly, the phase lock response of auditory nerve fibers results from the cyclic response of the inner hair cell, which is clearly present at low frequencies. Here we show low frequencies up to 1K and then 2, 3, and higher frequencies, where it disappears. The cyclic response disappears at higher frequencies, but there's still a large DC component. So the cell can, at high frequencies, the inner hair cell still responding, as does the auditory nerve, but it loses the cyclic AC component, which defines phase locking. Single unit recordings from auditory nerve fibers are plotted on the right in the form of period histograms. Here, the abscissa is one cycle of the sinusoidal input, here plotted in microseconds. The histograms show the preference for discharging over a range of phase angles, which gradually becomes less pronounced as we move to higher frequencies. So here we show 300, 400, 900, 1000, up to 1400 hertz. In the cat, phase locking essentially disappears above about 3 or 4 kilohertz. So here is Ramonica Hall's drawing of the projections of the auditory nerve fibers into the cochlear nucleus, showing how all auditory nerve fibers bifurcate and send one process into the DCN, BVCN, and one process into the ABCN. In the ABCN, there are some elaborate end bulbs upheld, which synapse onto the bushy cells in the BCN, which are the important topic for today. So you can see that cells in the VCN and DCN differ in the strength of the input from auditory nerve fibers. Furthermore, this schematic diagram shows that there's further difference in the elaborate circuitry in the DCN as compared with the VCN. We will actually only be concerned with the two flavors of bushy cells, spherical and globular bushy cells shown here, which receive that strong end bulb upheld input from the auditory nerve. So along with differences in the intrinsic properties of the cells in the DCN versus VCN, these differences produce very different response patterns, as shown in the next slide. Here we show how the posthumous time histogram and frequency tuning curves of high and low frequency cells, here high frequency, here low frequency cells that are phase locking. And this is typical responses in auditory nerve and how they're transformed by the different cell types in the cochlear nucleus. So really, as I said, we're really going to only concern ourselves with the spherical and globular bushy cells. But it's interesting to note how the other cells in the cochlear nucleus are transformed in very dramatic ways, both in terms of their frequency tuning curves and in their PST histograms. As we'll see, there are also some important differences in the low frequency bushy cells, those plotted here, versus their responses in the auditory nerve. This table summarizes the properties of cochlear nucleus cell types and their projections into the auditory brainstem by the trapezoid body or the various other acoustic strias. So note that the spherical and globular bushy cells exit by way of the trapezoid body and project to the major nuclei in the spirala, LSO, MSO, and MNTB. So let's digress for a moment and consider how stimuli are localized in different sensory systems. In the visual and somatosensory systems, space is encoded on the sensory epithelium, on the retina for vision, and on the body for somatosensation. The contralateral representation of space then is simply a matter of having the correct fibers cross the midline. But in the auditory system, the cochlea maps frequency, not space. So auditory localization requires a neural computation using acoustic cues. In the somatosensory system, touch input from the left hand reaches the right somatosensory thalamus and cortex, and by simply crossing at the midline, interestingly, the different modalities cross at different places. So light touch crosses in the medulla, pain and temperature fibers cross at their entry point in the spinal cord. In the visual system, an example of the contralateral representation can be seen as results of lesions of the right primary cortex, diagrammed here, which causes a loss of vision in the left visual field of both eyes, as shown here. This is set up at the optic chiasm by the nasal retinal ganglion cells crossing while the retinal ganglion cells on the temporal side do not cross. So on the motor side, cells in the right motor cortex control the muscles on the left side of the body by a decussation in the pyramids in the lower medulla. So note in all of these systems, the contralateral bias is established anatomically by projecting the axon to the correct side. But auditory space is set up by neural computation, not by anatomical projections. How's this done? To answer that, we have to look in the superior olivary complex. Here's Cahal's famous rendition of the superior olivary complex from Golgi preparations in the cat. You can see the three major nuclei, the lateral superior olive, medial superior olive, and the medial nucleus of the trapezoid body. Cahal also included the calyx of Held, an important synapse onto cells in the MNTB that will figure prominently later in this talk. So there are two circuits in the superior olivary complex, in the MSO and in the LSO, that are traditionally thought to encode ITDs or ILDs, respectively. Both originate from bushy cells. So cells in the MSO receive excitatory input from the spherical bushy cells on both sides, thus forming what we'll call an E interaction, excitatory. Cells in the LSO receive excitatory input from the spherical bushy cells on the ipsilateral side, but they receive inhibitory input relayed through an inhibitory interneuron in the MNTB that begins from the globular bushy cells projection to the MNTB. So we refer to this circuit as an IE interaction. And we'll see that it may be more appropriate to refer to these circuits as processing EE and IE rather than ITD or ILD. For the MSO, anatomical considerations would predict that the contralateral input will arrive later at the MSO than the ipsilateral, since it has a longer path length. Thus, you would expect the coincident cells in the MSO to respond best when the contralateral ear is leading, that is, if a sound source is on the contralateral side, to compensate for the longer conduction time. And this is what is almost universally found. In the free field, these cells in the MSO would be responding to sounds in the contralateral sound field. And MSO cells then project their axons to the ipsilateral inferior colliculus, thereby setting up a contralateral bias at that level. On the other hand, cells in the IE cells in the LSO are excited by sounds in the ipsi ear and inhibited by sounds in the contra ear. Therefore, they would be expected to respond preferentially to stimuli in the ipsi sound field. The nervous system converts that ipsi bias by sending those glutamatergic, presumably excitatory axons to the contralateral IC. Now in the cat, there are also a cohort of LSO cells that project to the ipsilateral IC. But some of these are glycinergic and inhibitory, as shown here, which would reinforce the contra bias in the ICC, while others, not drawn here, are glutamatergic. The result of all this is that cells in the ICC and higher centers would be predominantly, but not wholly, responding to sounds in the contra sound field. Note that in both the AVCN and in the superior olivary complex, some cells project ipsilaterally, some cells project contralaterally. Here for the AVCN, in the olive, in superior olive, there are ipsilateral projections and there are contralateral projections. So the anatomy itself is not enough to deduce the bias. One needs to know the physiology of the cells. Glendinning and Masterton and their colleagues referred to this complicated circuitry as the acoustic chiasm. Now, an additional complication is the MSO also receives inhibitory input from the MNTB and the LNTB, relaying inhibition from the contralateral and ipsilateral side, respectively. Now, the function of these inhibitory inputs to the MSO is highly controversial. And in the interest of national and international unity after 4 years of long national nightmare, I will defer discussion of this inhibition since I don't really have anything to add to this interesting question. So here's a nisosane section from one of our experimental animals in which an electrode penetration was made from the ventral brainstem through the different nuclei of the SOC. So in passing through the superior olive, one encounters many of the classic cell types. So for example, first you pass through trapezoid body fibers, which are monaural and driven by either ear, more or less randomly, and cover all CFs. Then you get to the MNTB, which cells are also monaural, but now driven only by the contralateral ear and at high CFs. In addition, these cells in the MNTB show a prepotential, a reflection of that large calycyl ending that they receive. Then, if you're lucky, you record cells in the MSO, which are binaural and have EE interaction, so therefore sensitive to ITDs, and predominantly low frequency. And finally, you reach the LSO, where you can see a lesion that we made in one of our experimental animals, where we recorded from a cell in the LSO. These cells are now IE, inhibited by contralateral ear, and sensitive to ILDs. And these cells in the LSO are predominantly high frequency, but if you get into this lateral limb, you will hit low frequency cells. So now let's consider the acoustic cues to sound localization. Along the horizontal dimension, space is computed using the two interaural cues of interaural time difference and interaural level difference. A sound to my right will reach my right ear slightly before it reaches my left ear, thereby creating an ITD, which can help encode its direction. Remarkably, the just noticeable difference for humans of ITD is 10 microseconds, extraordinary resolution. The sound to my right will also be louder to my right ear than to my left, provided that the wavelengths are short with respect to the dimensions of the head, that is, if they're high frequency sounds, so that the head can act as an effective acoustic shadow. So ILDs are predominantly a high frequency cue, and these constitute the so-called classical duplex theory of sound localization. Now, these acoustic cues can be quantified by measurements of the HRTFs, or head-related transfer functions, shown here for the cat for 5 points in space in the horizontal plane. So a microphone is placed near the tympanic membrane of each ear while playing a click from, in this case, 5 different points. The left and right ear signals are shown in blue and red. So for the point directly opposite the left ear signal arrives earlier than the right ear signal as expected, thereby creating an ITD. You can see that in the cat, this ITD is approximately 400 or 500 microseconds. It's also louder to the left ear than the right. It's reflected in the spectra, which are shown here. So the frequency spectra is higher, the gain is higher for the left ear than the right, and this is essentially the ILD function. Notice the ILD function is quite a complex function of frequency. A converse applies for sounds opposite the right ear, where the right ear signal arrives earlier and is louder. For sounds that are directly on the midline, the left and right ear signals are essentially identical, assuming a symmetrical head. So there are no ITDs or ILDs, that is, ILD, both variables are 0. So this is true for all points on the mid-sagittal plane. So even though we can discriminate whether it's the neighbor living in the apartment above us or below us that has the radio on. That is, we can localize vertically on the mid-sagittal plane. So that suggests there must be another cue that allows that discrimination when ITDs and ILDs are both zero. And there's now substantial evidence that the details of the spectra are a critical cue for vertical localization. And in particular, interest has been focused on this so-called first notch, which systematically moves in frequency as the sound source moves lower on the vertical plane. So I won't address the neural coding of these pinnacues, but we will touch on them briefly in a behavioral study later in the talk. So here's an example of how these HRTFs can be used to accurately simulate sounds in free field, so-called virtual sounds, which even produces percept that the sounds are outside the head. So this is a study of spatial receptive fields of cells in the LSO. So in the normal condition, the appropriate left and right ear HRTFs are used to filter the broadband noise and then delivered for 21 different azimuthal positions, varying on the horizontal plane from -90 degrees in the ipsilateral field to +90 in the contra field. The dot rasters plot 20 representations at each azimuth, and as expected, the LSO cell responds. So the sound is on from 0 to 200 milliseconds, right? Turned off at 200. And you can see there's a robust response when the sound is simulated sound is in the ipsilateral sound field and inhibition for sounds in the contralateral field. This is plotted below in the binaural normal response. So this confirms the statement I made earlier that cells in the LSO are responding to sounds in the IPSI sound field. So one of the advantages of using virtual stimuli is that we can easily demonstrate the effects of the contralateral inhibition by turning it off so that only the ipsilateral ear is stimulated. And here you see those responses plotted. And so you can see the effect of the dramatic effect of the contralateral inhibition to turn off the response when the sounds are in the contralateral field. Okay, so now let's discuss the processing of ITDs. And we'll begin by comparing the precision of timing in the auditory nerve fibers as compared to the bushy cells. We recorded from bushy cells by electropenetrations in the trapezoid body by recording from the axons. So we made a surprising discovery soon after we began making these recordings from axons of the bushy cells from the trapezoid body. The bushy cells were more precise than their inputs from the auditory nerve, despite the intervening synapse. So this slide shows a comparison of typical recordings from an auditory nerve fiber and a bushy cell matched in CF, so approximately the same CF, in response to pure tone stimuli at CF. So the dot rasters left and associated period histograms on the right show responses to 200 repetitions of that CF tone. Clearly, the bushy cell shows a more precise phase locking, as easily evident in these improved alignment of the dot rasters and the more sharply peaked period histogram. So phase locking is typically measured by the so-called vector strength, which we call R here, which is given here. The values are given here. So vector strength varies from 0, where the histogram is flat, to 1 when all the spikes fall into one bin. This shows a sample of period histograms for CF tones of 5 different auditory nerve fibers, 5 different spherical bushy cells, and 5 different globular bushy cells, approximately matched in CF. So going from low CFs, 300 hertz, to high CFs, 7 or 10 kilohertz. So the vector strength values are denoted here, and the CFs are denoted here. So clearly, you can see that this these low frequency spherical and globular bushy cells have period histograms that markedly differ from those of auditory nerve fibers. Now, at these low frequencies, you can't distinguish spherical from globular bushy cells because they're simply giving a phase-locked response. So to distinguish them, we recorded intracellularly from their axons and injected them with HRP to trace their axonal projection into the superior olive. And spherical bushy cells were defined as those axons projecting to the MSO, while globular bushy cells were at axons that had a calyceal ending in the MNTB. To compare the population of auditory nerve fibers and bushy cells, here we plot maximal vector strength as a function of CF. All auditory nerve fibers fall into the region defined by the two lines taken from the data of Johnson and confirmed by our own recordings from the auditory nerve. So no auditory nerve fiber ever had a maximal vector strength greater than 0.9. And so you can see that below 1 kilohertz or so, the majority of bushy cells have vector strengths that exceed that of auditory nerve fibers. So here we see example of a physiological specialization in a circuit that is computing ITDs. And obviously this specialization can enhance the temporal acuity of the system. Note that for both the auditory nerve and bushy cells in the cat, phase locking essentially disappears above about 3 or 4 kilohertz. Now let's consider the responses in the MSO and LSO. The classical description by Goldberg and Brown of MSO cells is that they are high-resolution coincidence detectors. This slide shows evidence for this from recordings in the MSO to tones at CF, for the cell conveniently 1000 hertz, as a function of ITD. Our convention is that positive ITDs correspond to the contralateral ear leading, as shown by this schematic. Clearly, the cell is very sensitive and modulated strongly by ITD with a cyclic response that has a period corresponding to the stimulus frequency, that is 1000 microseconds. So at each of the peaks in the response, the stimuli are in phase, just shifted by 1 complete cycle. This demonstrates that it is actually the integral phase, not the ITD, to which the cell is sensitive. While the cell responds best to binaural stimuli, it also shows a weaker response to monaural stimuli, shown by the arrows in the, down here, and plotted as period histograms on the right to contralateral ear alone and ipsilateral ear alone. These monaural responses are phase locked with a mean phase indicated by the downward arrow. And you can see, as expected from the anatomy, the ipsilateral input arrives slightly earlier, about 150 microseconds in this case. The coincidence model would predict that optimal response should occur if we give the contralateral ear a lead of that amount. And indeed, the peak of the ITD curve is approximately, but not exactly that amount. So this plot shows a test of the coincidence model for our population of MSO cells. On the ordinate here is the predicted phase from the monaural responses and the actual peak phase in the binaural responses. The model would predict that all points would fall on the 45-degree line, and you can see they're pretty close. Now, unfortunately, it has proven very difficult to record from the MSO. So most studies of binaural processing have been done in the central nucleus of the inferior colliculus, which is admittedly a poor surrogate for the MSO. Nonetheless, much progress has been made studying the IC. All cells in auditory nuclei respond over a range of frequencies. So it is of interest to look at the ITD curves for each cell over that range. So this slide shows a sample of 4 cells in the IC with each of the tone delay curves plotted on the same axis and normalized to the peak. In 1966, Rose, Gross, Geisler, and Hein proposed the concept of characteristic delay, which was defined as cells in which the periodic ITD curves for different frequencies reach the same relative amplitude. The CD would be the delay at which all of the ITD curves have a common peak, as shown by, appears to be the case in this cell, or a common trough in this case. For this cell, it's harder to say whether there's a common trough or perhaps a common peak or somewhere in between. And for this cell, even more difficult. So Shig, Kawada, and I indeed found it difficult to classify cells as satisfying characteristic delay by simply eyeballing responses such as shown here. So we came up with a way to quantify whether cells exhibit characteristic delay by making use of the well-known property that a system in which there is a time delay, the phase versus frequency function will be linear with a slope equal to the delay. So the test of whether a cell satisfies CD is whether the interval phase versus frequency plot is linear. To visualize these responses, it is easiest to consider a model with unnatural triangular ITD curves, as drawn here. So there are three models here, one in which there's a common peak, or a common trough, or a common point in between. Cells that have a linear interval phase versus frequency relationship are defined as exhibiting CD, and the value of the CD is given by the slope of the phase frequency plot. Here you can see for the one that has a common peak, we have a slope that corresponds to the value of the common peak. Furthermore, the phase intercept, what we call the characteristic phase, is 0. So the CP tells you where the common point is. If the common point is at the trough, then the phase frequency plot is also linear, but now has a CP near 0.5 corresponding to one input out of phase. And again, the slope of the line corresponds to the point of the common trough. This cell has a common amplitude, but its characteristic phase now is not 0 or 0.5, but rather somewhere in between. And again, the slope corresponds to the point of that common amplitude. So if we go back now to the example shown on the previous slide, the interval phase versus frequency analysis are shown in red, with the point of CD plotted by the arrow. As expected, this cell, which appeared to have a common peak, has a CP near 0, and the common peak occurs at about 113 microseconds, corresponding to where one would eyeball it. This cell, which appeared to have a common trough, has a CP near 0.5, and the CD corresponding to approximately that point. This cell had a linear phase frequency plot, but its CP is not 0 or 0.5, but somewhere in between. And one would be hard pressed to identify this point as the common point. Finally, this last example had a nonlinear phase frequency plot, so it did not satisfy characteristic delay by this definition. Now, pure tones are rarely heard in nature. More natural but well-defined signal is broadband noise. So this slide shows responses of 9 inferior Cliquot cells to ITDs of broadband noise, shown by the solid line and the asterisk, plotted compared with the response predicted from its response to pure tones obtained by simply averaging all of the individual tonal curves. That's given by the dotted line. So you can see for these 9 cells in the IC, there is a surprisingly good correlation between these two measures. So the response to broadband noise can be predicted from a linear summation of its response to pure tones over the bandwidth of the noise. Now, if we do CD analysis on cells in the superior olive, so here's an example from the MSO. We can see that the cell in the MSO appears to have a common peak. If you look at these, we didn't normalize the peaks in this plot. And the CD analysis shows a CP near zero, a slope of 33 microseconds, which is very close to where the noise delay curve has its peak here, in this case, at 36 microseconds. Low frequency LSO cells are also ITD sensitive and show a characteristic delay with a CP now near 0.5 as expected. And you can see the slope of the line predicts a characteristic delay common trough at about 500 microseconds, which is close to what we found with the noise delay curve. Now, most models of binaural hearing incorporate cross-correlation to mimic the coincidence in the MSO. Here, we wanted to test this idea by studying responses of cells in the inferior colliculus to noise stimuli that differed in the degree of interaural correlation. So we generated noise stimuli by starting with two independent noises, call them A and B, delivering A to one ear and some combination of A plus B to the other with different ratios of A and B. We could thus generate noise stimuli with interaural correlations between 1, which identical noises to the two ears, so A to both ears, or 0, A to one ear, B to the other, or any value in between. In addition, we could generate interaural correlations of -1 by delivering A to one ear and -A to the other. So you can see that this ICC cell responded with a systematic change in the degree of modulation as the interaural correlation changed from 1 to 0. And when the interaural correlation was -1, the response is essentially 180 degrees out of phase. So the plots on the right show for a sample of 10 cells in the IC, plots of degree of modulation as a function of interaural correlation. And you see a very systematic relationship for every cell. So this is exactly what you'd expect out of a machine that's computing cross-correlation. In addition, we examined the effects of delivering the same tokens of noise, but phase shifting the noise to one ear. By digital filtering, we phase shifted the noise to one ear in increments of 1/8 of a cycle. So here's the normal response, identical noises to 2 ears. Now phase shifting the noise to the ipsilateral ear by 1/8 of a cycle, 1/4 of a cycle, 3/8 or half a cycle, or phase shifting by 1/8 to the contralateral ear, 1/4 of a cycle, 3/8. And similar manipulations are shown down here. You can see the remarkable machine-like properties of the two ICC cells under the 8 different conditions. Basically, all ITD-sensitive cells we tested in the IC behaved in a similar way. So the nervous system appears to achieve this high-resolution ITD sensitivity by employing a process that is very similar to the mathematical process of cross-correlation. Interestingly, naval engineers working on a similar problem to localize submarines in open ocean have developed methods which also involve cross-correlation from wide underwater microphone arrays. So the brain seems to use a technique which is similar to what humans have developed, human engineers have developed. Okay, now let's move on to ILD sensitivity and the LSO. Well, we know that classically LSO cells are known to be sensitive to ILDs, but I've shown you that they are also sensitive to ITDs. I showed you an example of a low frequency LSO cell that's sensitive to ITDs, pure tones. I didn't have time to show you evidence that high frequency LSO cells are also sensitive to ITDs, providing you give them a time varying envelope, for example, like a AM stimuli. So when stimuli are delivered in free field, what is the relative effectiveness of each of these three acoustic cues, ITDs, ILDs, and spectra? So we made use of virtual acoustic stimuli to manipulate each of the three cues in isolation to study that question. So for each point in space, there is an unique ITD, ILD, and spectra combination. With digital manipulation, we can set one of those cues to be constant while the other two vary, or we can vary that one cue while the other two cues are held constant. So this shows you responses from a single LSO cell, and each panel shows results of manipulation of one of those cues, ITDs, spectra, or ILDs. So for example, this panel here, manipulating ITDs, we see first the normal response, filled circles, shows the expected response in the ipsilateral sound field. And that response is plotted in each of the three panels. The red delta ITD response is obtained by varying ITDs while holding the other two cues constant to their values at 0 degrees. And you see that response is unmodulated. While the open circles show responses when ITDs are held constant and the other two cues are varying. That response is nearly equal to that of the normal, right? So both of these results suggest that ITD is not a salient cue for the cell. Similarly, the responses when we manipulate spectra in analogous ways, you get the same kind of similar responses, right? On the other hand, when only ILDs are varied, the red curve, you can see a response which is very similar to that of the normal. And when ILDs are held constant, the cell is unmodulated. Right? So these results suggest that ILDs are really the salient cue. Right? And generally speaking, the population of LSO cells we studied behave similarly. So the conclusion of this experiment was the rather boring one, that ILDs are the most salient cue for LSO cells, which fits the classical view. So if that's true, then why is there the largest synapse in your brain in this circuit? So the calyx of Held has become a model system for studying the biophysics of synapses. Yet we don't understand why such a highly specialized structure has evolved in a circuit that appears not to be dependent on temporal effects. So the answer to this might be found by looking at responses of the LSO to ITDs of transient stimuli, such as clicks. So ITD functions to clicks in the LSO have a plateau with a narrow window of inhibition when the contralateral inhibition is timed just right to inhibit the ipsilateral excitation, as shown by the schematic up here. On either side of this window, the excitation arrives either too early or too late to be inhibited. So note the very steep ITD sensitivity of this LSO cell along both sides of this temporal window. This cell also illustrates one of the remarkable features of the IE interaction in the LSO, namely the contralateral inhibition arrives nearly synchronously with the IPSI excitation, even though it has to travel farther and has an additional synapse. So Boudreau and Tucitani in their seminal studies of the LSO had already made this observation, since repeated by many others. So the calyx of Held may serve to minimize the delay of the contralateral inhibition to the LSO and make it exquisitely sensitive to ITDs of transients. Okay, I will finish by describing some of our behavioral studies of sound localization. We trained cats to look at visual and auditory targets. The cat faced an array of speakers. Each speaker had an LED at the center, of course, so corresponding visual or acoustic targets could be presented. Eye position was monitored by suturing a small coil of wire on the eyeball and placing the cat in an alternating magnetic field set up by coils embedded in this cube. And we simply use techniques that are developed by oculomotor physiologists. The cats worked for a food reward under operant conditioning, and eye position was continuously monitored under computer control. And the reward was delivered if the eye position was within an electronic window centered on the target. So typical trials began with an LED straight ahead turned on. Cat looks at the LED, and after some delay, unpredictable delay, the target is turned on and the cat orients to it. So we initially did the experiments with the head fixed, but we soon found that localization performance was much better when the head was free, and we measured gaze or eye position in space. Right? So this shows the eye movements to visual stimuli on the left, auditory ones on the right. The fixation LED is on until time 0 when the target is turned on. The location of the targets are given by the little arrows on the right. Visual trials are shown on the left, auditory on the right, and we plot here now the vertical gaze shifts to stimuli varying in elevation on the vertical axis, or horizontal gaze shifts to targets varying in azimuth. You can see that the saccades to both visual and auditory targets are both very accurate and precise. Right? They hit the target, and there's relatively little scatter. And these are quantified in the next slide. So here are scatter plots of localization of short and long duration visual targets, short and long duration auditory targets. And we plot the vertical gaze shifts to the targets varying in elevation, horizontal gaze shifts to the targets varying in azimuth. And the targets are color coded. So the gain or regression line of the responses shown by the red line is a measure of the accuracy of the gaze shift. And that's given by the slope of the regression line. Perfect performance would be a slope of 1. The delta value measures the precision or the distribution of responses about the mean and is computed as the standard deviation of the residuals. So in general, performance is better for the long duration targets than the short for both visual and auditory cases. And it's slightly better for visual stimuli than it is for auditory, although that difference is relatively minor. So this slide compares the performance of one of our cats to some other sound localization measures in other studies in the barn owl and 2 studies in human. So it looks like our cats are able to localize just as well, or maybe even better than these other subjects. All of the responses are plotted on the same scale here. Now, to test the effects of spectral cues, we studied localization of narrowband noises, 1/6 octave wide, centered on 6, 8, 12, and 16 kilohertz in the region of the first notch. So these narrowband stimuli will have impoverished spectral cues while maintaining ITDs and ILDs. And here we plotted the scatter plots for vertical and horizontal targets separately, just for ease of looking at them. The azimuthal localization is degraded. You can see that these slopes are not quite as good as it is for broadband noise. But they're pretty much near normal. But vertical performance is significantly worse. Right? The low gain values for vertical localization. In fact, the cats look like they're essentially guessing in some of these cases. So this supports the idea that spectral cues are crucial for localization and elevation. So let me conclude with some observations about what the cat is doing with its pinna while localizing sound. So first, we examine pinna movements when the head is held stationary. So here's a short video taken while the cat is working on the visual localization task, so you can see the target. We pasted some white markers on the edges of the pinnas just to help you see the movement. And all the trials begin by turning on the LED straight ahead. And you can see the cat orients to it and then moves in a consistent way depending on the location of the target, which is indicated afterward. So watch the right ear and try to predict which direction the target was. Noteworthy is that the cat is being rewarded for its eye position, which you can't see, but not for pinna position. It can do whatever it wants with the pinna and still get a reward. But you can see that you can predict the position of the target simply by watching the pinna, which orients to all the targets except those on the contralateral side. So to quantify these pinna movements, we surgically implanted a coil at the back of the pinna. So that in addition to the eye coil, we had a pinna coil. Here are plotted the movements of the eye on the top and the pinna, the vertical component and the horizontal component of the pinna movement on the bottom. In these trials, the target was turned on before the LED went off. The cat was trained to make the saccade after the LED was turned off. And you can see that, again, the eye position is quite accurate to the target, and the pinna moves consistently to rightward for this rightward target, both visual and auditory stimuli. One difference is that the pinna moves for the visual stimuli about the same time that the eye moves, but for the auditory stimuli, the pinna moves right away and with a second movement when the eye moves. So an important point is that, as we saw in the movie, the pinna responses are consistent and reproducible, even though cat was not being rewarded for moving the pinna. Now, what happens when the head can move? Since the pinna rides on the head, it should turn when the head turns, unless there is some compensation. Now we have three coils, one on the eye to measure gaze, that's the green trace, one on the left ear, blue trace, and one on the head, the black trace. And in addition, we calculate ear on head by subtracting the head from the ear position. You can see that the ear moves first, right, and maintains its position towards the target, even though the head, which is moving slower with a slightly longer latency, even though the head is moving. So the only way it can maintain its position in the face of the head movement is by counter-rotating the ear on the head. If we take the peak ear on head velocity and divide by the peak head velocity, we can calculate a gain of we call this the vestibulo-auricular reflex. This gain, in this case, is nearly perfect compensation of -1. So we call this the VAR because it shares many kinematic characteristics of the well-known VOR, vestibulo-ocular reflex, in which the eye counter-rotates to compensate for the head movement to keep the retina stabilized in space. So the ear must counter-rotate on the head to maintain that constant position. So the VAR differs from the VOR in that it is only active for head movements towards the ipsilateral side. And it's simply easiest here just to look at the red traces. This trace is what I showed you on the previous slide. So these are 6 targets varying in azimuth. You can see that we're measuring the left ear, and for all the 3 targets on the left side, we see this compensatory VAR. But when the targets are on the right side, the ear simply rides with the head, and there's no VAR. So not shown are some control experiments in which we passively rotated the head and saw that the VAR was still active, thereby suggesting it is vestibular in origin and not to an efferents copy. So it's not every day that one can discover a new reflex. So I'd like to conclude by acknowledging the many wonderful colleagues, students, postdocs, faculty on leave that I've worked with over the past 40 odd years. They are really the ones responsible for this work. I've also been blessed by working with the faculty and staff of the Department of Neurophysiology at the University of Wisconsin, as it was named when I first joined, who educated me on all things auditory. Also, I thank NIH and NIDCD for funding the research over these many years. Thank you.
Wow, thanks, Tom. That was absolutely beautiful. I can hear you talk about your work always and forever, and that was such a really beautiful presentation. And I know that because we'll have it available online, people will be able to view it again and again and again. So absolutely wonderful. But I know you can ask questions in the chat, and Tom can look at those and respond individually or to the group. So that's a really great method that we have here for asking questions sort of online, offline. But Tom, I'm handing you the certificate virtually, and you'll have it at home or in your office. And congratulations again on this amazing Lifetime Achievement Award. Okay, so our next set of awards fall into a new category. This is our inaugural Pioneer Award in Basic Sciences. And the awards committee decided to give this award jointly to 3 pioneers, Jeff Holt, Gwen Gilliak, and Andy Griffiths. And this is for their joint work leading to significant advances in hearing and vestibular science, the identification of the ion channel proteins that sense sound and head motions in the inner ear and water displacement in lateral line organs. It gives me such tremendous pleasure to present these awards to you, 3 amazing pioneers in our field. This is what your certificates are going to look like. And I will now like to invite Matt Kelly to talk about our award recipients today, and then we will hear from each of them.
Thank you, Ruth. So in thinking about this, right, this is an award, a new award that was created largely under the hard work of Ruth Ann Etok when she headed the awards committee. And the idea was behind the Pioneer Award in Basic Science is to recognize a significant advance in hearing vestibular related research. And I can't think of a more appropriate advance to represent the inaugural Pioneer Award than the discovery of the hair cell transduction channel. So this was really one of the holy grails of, certainly the holy grails of hair cell science, and probably really all auditory research, was understanding how this mechanotransduction channel worked. And it was really collaborative work between these 3 individuals, Jeff Holt, Gwen Gilliak, and Andy Griffith, that revealed what the actual nature of the molecule is that modulates hair cell transduction. So really briefly, the story starts in the late 2000s when these 3 great researchers started working together to try and understand the deafness in mice that had a mutation in TMC1. And there was a confusing issue, which was that while these animals were deaf, their vestibular system seemed to be fine. And so it really wasn't clear how this could be the transduction channel if the vestibular hair cells were working perfectly well. And it was one of their first works that demonstrated that TMC2, or related molecule to TMC1, actually compensates for and can also work as a transduction channel. And so the first publication in 2011 demonstrated this redundant role for TMC2. And they suggested very modestly in that paper that they thought this could have important implications as a key component of the transduction channel. They went on to very elegantly demonstrate that, in fact, TMC1 and TMC2 can both function as mechanotransduction channels in hair cells. And the subsequent work has just been phenomenal in terms of elucidating not just the molecular nature of these molecules, but how they work at a structural level to allow mechanotransduction to occur. There's still, certainly Jeff and Gwen are still working on this project really hard and are making really exciting innovations every day about understanding how hair cell transduction works. The last thing I'd say is, the The publications from these labs are consistently fantastic. They're innovative and of the highest quality. And I always read their papers with great excitement because I know it's going to be something super insightful and really clever as well. So I really can't think of a better group of people to be awarded the first Pioneer Award. So as we did before, please raise a glass or whatever you have for Jeff, Gwen, and Andy, and I will pass the Zoom room over to them to talk about TMCs.
Thank you, Jeff. And thanks to Matt for really terrific introduction. Thanks for nominating us. And I could not have summarized it any better. That was really fantastic. And thanks to the ARO for this award. I know this is a big honor for me, and I'm sure it's a big honor for Jeff and Gwen as well. So, okay, so this story starts out actually before the turn of the century, and it started with my mentor and colleague, Tom Friedman, and he and I traveled all over North America, ascertaining this family you see, segregating really severe progressive sensory neural hearing loss. And Tom used this as an opportunity to get back in the lab. So when we were done collecting the family, he actually genotyped them himself. He found that the deafness was segregating with markers on chromosome 9, and you can actually see the genotypes on this slide. So it turns out that that was the same region of chromosome 9 where NIDCD had previously mapped a recessive form of deafness called DFNB7, and that had been before Tom and I arrived on the scene. It was led by Ed Wilcox. And of interest, this locus was located on a region corresponding to chromosome 19 in the mouse, where this mouse deafness locus was known to reside. So this was great for us because it offered more families to help us hunt for an underlying gene. This family you're looking at here is one of the original ones used to map DFNB7. In the interim, when Tom came to NIDCD, he established a really strong relationship with Dr. Sheikh Riazuddin in Lahore, Pakistan, and that started a long history of really outstanding scientists coming to NIDCD to train, including Zubair, Sadaf, and Saima, who many of you know. And so Saima and Sadaf actually, in the course of their training, had ascertained dozens of families, many of which we used because they were shown to be linked to DFNB7. So we had a total of 11 families segregating recessive deafness linked to this locus, in addition to our original family, LMG 128. And so this is a good situation to be in. So just an aside here on the deafness mouse, as Matt pointed out, this mouse was described in the 50s by Dale and Coker, and they noted that it was the only deafness mutant that didn't seem to have abnormal motor vestibular behavior, and they thought that that was unusual and important, and they were right. In 1980, Karen Steele and Gregory Bach published a further analysis of this mouse, and they noted that they couldn't detect microphonic potentials, even though the hair cells seemed to be structurally intact. And so they posited that maybe the underlying defect had to do with ion channels not opening. And again, that turned out to be prescient. The last contribution to note before we move on is Branya Keats in LSU had been working on mapping this locus, and she'd shown that it was located on mouse chromosome 19, again in the region corresponding to DFNB7, and now this new locus, DFNA36. So at this point, Tom had many genes to work on in his lab, and he generously offered this to our lab, and Kyoto Karima was a staff scientist in the lab and extremely talented. You will see his name throughout this talk. At this time, the human genome sequence was incomplete and not assembled, and it was literally like looking for a needle in a haystack. Kyoto cleverly sifted through all those pieces of DNA by seeing if they corresponded to any other DNA in the genome, with the idea that if they did, it was likely coding sequence, and that's the DNA you want to sequence. And sure enough, he found a bit that corresponded to chromosome 20, and we now know that that chromosome 20 bit was TMC2, as we call it now. And that was what led to Kyoto's really breakthrough. And once he found those bits of DNA, he quickly found mutations. He stitched the sequence and the gene together from all those pieces of hay and came up with this genomic structure TMC1 here, and showed mutations in every single family segregating hearing loss linked to this locus. And so the recessive families were segregating alleles that clearly wouldn't encode a functional protein. They either had big deletions or frame shifts or premature stops. The only and in contrast, the family with the dominant mutation, they segregated a missense mutation called D572N. And that was important because we know from the genetics that this allele must act by a dominant negative or gain of function mutation, which we knew would be important if we ever got to the point where we knew the function and could test it. So Kyoto also went through and figured out the mouse TMC1 gene, again, stitching it together from bits and pieces of cDNA and genomic DNA, and came up with the genomic structure of mouse TMC1. He worked with Branya's group to show that the deafness mouse was deaf because there was this deletion of exon 14. And so this was really convincing genetic evidence that we had the right gene. We called it transmembrane channel-like because it was predicted to encode a protein with lots of membrane spanning domains, which you can see here with the green bars above these aligned sequences. So these show the predicted amino acid sequences of mouse and human TMC1 and TMC2. And again, Kyoto painstakingly assembled these from the bits and pieces of genomic DNA and cDNA. And this also shows that yellow region is deleted in the deafness mouse. This region here with the D highlighted in yellow, that's our missense substitution. And this was really remarkable. So these were so closely related that in our paper, and this comes from the paper we published in Nature Genetics, we actually speculated that the lack of a vestibular phenotype, exactly as Matt said, associated with TMC1 mutants might be because TMC2 is contributing to the function in the vestibular system. And that is a really important concept to unlocking what the function of this gene was. So one of the groups trying to identify the gene in this region was a team led by Kieran Steele. And this included Corne Kroos, and they did beautiful phenotype work on this mutagenesis-induced mutant called Beethoven. This was really a semi-dominant mutant. And Karen Overham was working with them to try to find, she mapped the locus and was trying to find the mutation with her student, Sarah Vrugdi. Kyoto made it really easy for them and gave them the primers and conditions, and they were able to find this missense substitution in the TMC1 gene. And as you'll see from Jeff and Gwen's talk, this turns out to be a really invaluable resource. But what was a little confusing to many of us was Walter Marcotti and Corne published a paper later, I think it was 2006, and testing this hypothesis that maybe TMC1 encodes the transduction channel. And you're looking at transduction currents measured from deafness mice and Beethoven mice. And you don't have to be a physiologist to see that the currents are there. And that really didn't seem to support the idea that TMC1 might be part of a transduction channel on hair cells. And so this pretty much threw the whole field off the track. This idea that TMC1 might be a transduction component was radioactive. I couldn't find people to work on this idea in my own lab for a while. Our tack was really, though, not to test that hypothesis. We were interested in this gene family and the proteins and what they might be doing, no matter what that was. And so again, Kyoto painstakingly identified this whole gene family of 8 mammalian paralogs. These show the human and mouse proteins. I want to shout out to Stefan Heller, whose group also did essentially the same thing. Stefan was curious about the role of these in transduction as well. You can see all of these encode multipass transmembrane domains, which are shaded in these diagrams. Our approach was to make knockout mice for mouse TMC1 and 2 to get at the function of these genes, but we also had made knockouts for TMC6 and 8, and I don't have time to tell you about that today, but I'd be happy to have a chat. So we were also trying to make antibodies, see where the TMC protein was in hair cells, trying to express the protein in tissue culture cells. None of it worked. And some of it was kind of circular in that it was hard to make progress in one front without progress on the other. It was really depressing. And almost 5 years went by of wandering in the desert. I made several trips down to my colleague, mentor, and mental health support person there, Tom Friedman, and told him several times I was ready to quit. And I was ready to quit. And Kyoto kept telling me we ought to be working on something else, but we stuck at it. Our litmus test was we would see what happens when we cross the TMC1 and TMC2 mice together. And this is what happened. I remember this day distinctly. It was maybe the best scientific day of my life. Kyoto came back up from the mouse room. We had our first litter of double knockout mice, and he said they were not righting themselves when he flipped them on their back. They didn't have the normal reach response of a wild type mouse. That's what you're looking at right here. And so for me, that was a nirvana moment. It was like seeing water in the middle of the desert. And so at that point, I reached out to Jeff and Gwen. Jeff had several years earlier offered, to help if we had anything that he could, help out with. And I told him for several years that we're waiting for this double knockout. And this phenotype in the double knockout, which we didn't see in the TMC2 knockout, told us that TMC1 and 2 were interacting in vestibular hair cells. And I just had a hunch that this was going to be what we needed to proceed on this project. So the first thing we did, we worked with Charlie, and you're going to hear from Charlie later, so I don't have time to talk about his contributions to our project, except they were really important. Kyoto and Yoshi Kawashima, who is an otolaryngologist working with us in the lab, used a LAC-Z reporter from the knockout construct, which they made to track RNA expression from TMC1. And so these are some really beautiful figures that they made showing that the gene is expressed in the vestibular end organs and, interestingly, predominantly in the peripheral zones. As far as TMC2, the construct didn't work for technical reasons. We had aberrant splicing. So our colleague Doris Wu and Mike Mulheisen in her lab did this really beautiful in situ hybridization showing that TMC2 RNA is expressed in early postnatal hair cells. So in the cochlea, this is a LAC-Z reporter for TMC1 in the cochlea. You can see it's expressed in the 4 rows of hair cells, both with the surface view and with the axial section through the cochlear turn. So this was good to know that these genes were expressed in hair cells. And Yoshi actually did these experiments on the right, and I will say these were done with input and knowledge from Jeff and Gwen, who were meanwhile making lots of progress on the physiology, which you'll hear about shortly. But the upshot of this is that these cochlear hair cells in the double knockout mice on the right don't take up this FM dye, which is sort of a proxy for mechanotransduction. And that was in spite of the fact that the hair cell stereocilia looked reasonably intact with reasonably intact tip links, suggesting that this was likely a physiologic defect, maybe a developmental defect, but not a gross structural defect. So the last part of this puzzle was really figuring out, are these proteins in the right part of this hair cell at the right time to be involved in transduction? We'd struggled with antibodies. Kyoto made these transgenes where he inserted in these fluorescent tags into genomic clones encoding TMC1 and 2 and used those to make transgenic mice. And so it was really important for Jeff and Bifeng Pan, who worked with Jeff, to show that the cells in these mice worked normally, and they showed that the hair cells did function normally and weren't screwed up by these fluorescently labeled TMC proteins. And Kyoto then became a regular inhabitant of Bashar Kashar's lab, where he worked and showed that these fluorescently labeled proteins show up at the tips of shorter stereocilia and even some microvilli, both in cochlear and vestibular hair bundles, which is the right place and right time if your prediction is that these are involved in transduction. And so with that, I hope I didn't run too far over, and I'm just going to pass the baton to Gwen.
Thank you, Andy, for such a beautiful introduction of how we got there. So, you know, I'm truly honored to be here today to receive this award from the Association of Otolaryngology. And here's a quote from Vincent van Gogh, who said, "The great things are not done by impulse, but by a series of small things brought together." And I think this really is, you know, summarizing well the discovery of TMC1. So my key contribution to this work took place in December 2008. That's when we started working on the mice that we received from Andy Griffiths. And, you know, I have to say at that time, we had analyzed mechanotransduction currents in many mouse models, and a large number of them came from collaborators. In many cases, they would appear to have preserved mechanotransduction, and the project would not go anywhere. So the lab folks were a little bit burned out. And when we received those mice from Andy Griffith, who were at the University of Virginia, and all our electrophysiologists turned down the idea of doing this work, they were burned out. But, you know, I was interested to try it out. And it turned out to be a very epic week. So the pups were born on Sunday, and on Monday, I made new solutions and I started the recordings on utricular hair cells on Tuesday. As you can see here, I recorded from 3 different mice, and the hair bundles in each cases looked pristine. I was looking at the utricle, transduction looked just fine, and Jeff took the tissue to the confocal microscope, imaged them, and told me the FM looked pretty normal. On Wednesday, I continued and recorded from 2 new pups from the same litter. Again, you know, normal transduction current and normal FM uptake. Same scenario occurred on Thursday. Normal transduction currents, well-looking bundles, everything was fine. So at this point, I was convinced, okay, this was another project that just was not going to go anywhere. But on Friday, the first pup I recorded from, coming from the same litter, showed pristine bundle again, but no mechanotransduction currents. So I got convinced I was doing something wrong. Jeff took the tissue to the confocal, and he came back and said there was no FM uptake. What did I do wrong? I wondered. The bundles look great, the cells look great, the voltage-dependent currents look great. Did I use a wrong solution? So I went ahead and redid my solutions and moved to the next mouse. Same story. No transduction currents, pristine-looking hair bundles, no FM uptake. So we sent the tails to Andy and waited patiently for the results, wondering what this was about. And the results came in the following week. And what we found out is that the mice that I had recorded from Tuesday, Wednesday, and Thursday all expressed TMC2. And just by chance, the 2 mice I recorded from Friday, on Friday, both lacked TMC1 and TMC2. So it was a, haha moment of, okay, there is something to it. We landed on something interesting. So as we continued the work, we confirmed that utricular hair cells from double knockout mice had no transduction currents in the utricles. Cells that lacked TMC1 had normal currents, again, looking at neonatal cells, and cells that lacked TMC2 had smaller currents. And we validated this on several mice and large number of cells. We also looked at transduction phenotypes in outer hair cells. This was work done by Andrea Lely. And again, we found a similar trend. Double knockout mice had no transduction currents. Mice that lacked TMC1 had normal currents, neonatal mice, and mice that lacked TMC2 had smaller currents. This was done on basal cells, basal outer hair cells, but we found the same trend in apical hair cells with a slight delay in the phenotype. And again, we validated this on a number of cells. So now to take a little step back, we had done a lot of work characterizing mechanotransduction and acquisition of mechanotransduction over time and along the organ of Cody, going from the base to the apex. Again, that was work mostly done by Andrea Lely. And the idea was whichever protein encoded for the mechanotransduction channel had to be expressed before or around the time that transduction was acquired. So this was a lot of work that was done by Andrea. And we determined that mechanosensitivity in outer hair cells was acquired tonotopically from around P0 in the base to around P2 in the apex. The spatial temporal pattern of acquisition of mechanotransduction became really a treasure map, a pattern that we started looking for to get a clue as to which protein might be the key player in mechanotransduction. Here's my treasure map. So, we looked at a lot of different channels, and this is here some of the work that I'm illustrating that was done by Yukako Asai. And we and many others were interested in TRIP channels because TRIP channels were known to be the channels of the senses. They shared many properties of the mechanotransduction channel. And so for this reason, we suspected they may be involved in hair cell transduction as well. And so we analyzed expression of 33 TRIP channels, and we added also 3 PKD channels. And these plots here below are showing quantitative RT-PCR done for all of those channels. So there was a massive project that was done by Yukako. And no matter how we looked at the data, really none of them seemed to demonstrate a trend that matched well with acquisition of mechanotransduction, including TRIP-A1, which we and others had looked at as a potential candidate for mechanotransduction. So then we look back at TMC1 and TMC2. So again, plotting a map of mechanotransduction current acquisition, the spatial temporal pattern that we were looking for. And we were intrigued to see that indeed, when we looked at TMC2 expression, we found really a similar trend in expression, with acquisition in the base initially and progressing towards the apex. Interestingly, when we look at TMC1, we found that there was a delay in expression of TMC1. And indeed, that's what we demonstrated. We found out that there was a switch from TMC2, which was initially expressed. So this is here showing you data from the base. TMC2 was initially expressed at the time where transduction was acquired. But its expression really went down pretty quickly after that over the next 4 postnatal days. At the same time that TMC2 expression decreased, TMC1 took over. And we saw the same in the apex. So this was very interesting. And that was really what led us to think that TMC may actually be the mechanotransduction channel. And it also explained how this beautiful work done by Walter McCarty and Connie Cross, who was one of my PhD mentor, where they demonstrated that DN mice and Beethoven mice actually add normal mechanotransduction initially, and eventually add changes in the voltage-dependent expression, in the expression of voltage-dependent channels, but transduction was not altered. So this really, this switch from TMC1 to TMC2, sorry, from TMC2 to TMC1 explained the data that they were seeing and how we got off track from that. So going back to my introduction, really a succession of small things linked together can lead to great things. And I feel like I was there, at the right place at the right time. So before I pass the baton to Jeff, I just wanted to tell a little bit more about TMC1 and TMC2 and their role in the vestibular organs. And I feel that we've learned a lot over the past 10 years or so about the role of this channel in the auditory organ. But there is a different story in the vestibular organ. So for example, that switch from TMC2 to TMC1 does not occur in the vestibular organ. Instead, we see that TMC2 is expressed throughout the lifetime in mice. At the same time, we see that TMC1 is much more largely expressed in the vestibular organs than TMC2 is. Work from Charlie De La Sentina, who's actually getting the Innovator Award, has demonstrated that angular VOR are absent in double knockout mice. And indeed, we see a behavior, right? We see the mice spinning as that was shown by Andy earlier. But we also see that there are altered VORs in mice that lack TMC2, okay? Now there's new data from our lab, and I invite you to come and see the poster from John, my student, on Wednesday afternoon, that show surprising data. This is looking at linear VSEPs. And not too surprisingly, mice that lack both TMC1 and TMC2 lack VSEPs. But, and mice that lack TMC2 in purple here have altered VSEPs as well. But mice that lack TMC1 actually lack VSEPs. And we repeated these recordings many times thinking we were doing something wrong. But this is illustrating that TMC1 actually plays also an important role in the vestibular organs. And perhaps TMC1 and TMC2 play different roles in otoliths and semicircular canals. So something to be continued and something we're definitely interested in. So I would like now to finish my presentation by expressing my sincere thanks to the ARO Award Committee and all those who put my name forward for this award, as well as everyone who contributed to this work. I am deeply honored and I am grateful to receive this award along with Jeff and Andy. And I do hope that this will inspire young women scientists in the future. And with this, I would like to pass the baton to Jeff.
So yes, I would also like to begin by thanking ARO for this recognition. I want to thank, of course, the nominators who took the time to write letters on our behalf. And I want to thank the awards committee for selecting us for this. I'm particularly pleased that the committee decided to select a collaborative team to receive the Pioneer Award. You know, I just think it's really important to recognize the invaluable contributions of collaboration and how it helps to advance science. So I hope that that's a tradition that will continue, recognition of collaborations. I'd also like to carry on with the format of Gwen and Andy in that they were sharing stories behind the science. And for me, the story of TMC1 really begins when we first moved to the University of Virginia, which was in the fall of 2001. Gwen and I were setting up our new lab there. And it was at that time that, well, it took a couple months to get the physiology setups going and get everything working. And about, I think, winter of 2002, when we got our first physiology setups working. And that's right when these two papers came out. Andy's paper, the Karen's paper, talking about the TMCs. And this really caught my attention. And as we're there, Gwen and I thinking about what we're going to focus our new lab's work on, it struck me that this was going to be something of interest. And so I picked up the phone and I called Andy, and he was very receptive and enthusiastic about the idea. He said, Jeff, I'd love to collaborate on this. We're going to make some new mice and we'll get back in touch as soon as those are ready. So you've heard this story now. That led to the publication that came out in 2011, and I'm not going to belabor that. But at the end of this publication, we concluded that one hypothesis to explain the results was that TMCs 1 and 2 are required for trafficking, assembly, structure, or function of the mechanotransduction complex. Of course, our favorite hypothesis was that TMCs were forming the hair cell transduction channel, but we really couldn't rule out any of these other possibilities either. There was even some criticism in the field that maybe we shouldn't publish this early, that maybe we should have waited for definitive proof. But we felt that it was going to be a long time in coming before we really had the proof, and we wanted to get the idea out there and present our hypothesis and the data and really let the field take a crack at it. So we did, and we spent another couple years working on this and came out with this paper in 2013. And for me, this was really a eureka moment. When we started looking at the reversal potentials in cells that were expressing TMCs, just TMC2, just TMC1, or TMC1 with the Beethoven mutation. We found that these had different reversal potentials, and we could do some simple calculations and realize that there was a difference in calcium selectivity, particularly with this Beethoven mutation. That single point mutation led to a decline in calcium selectivity. And as an electrophysiologist, this is one of the hallmarks of an ion channel. So that really caught my attention, and I began to become convinced that TMCs were at least a major part of the hair cell transduction complex. But yet again, there were skeptics who were concerned that, well, maybe this mutation could have been in an accessory protein. TMCs were accessories, and maybe that could cause some allosteric change in some primary pore-forming subunit. And I agree that was a possibility. I didn't think it was as likely, but it did send us sort of back to the drawing board, trying to gather more data. So we spent the next 5 years, and we eventually came out with this publication in 2018 that I think really nailed it down with some more definitive evidence. And so this work was led in my lab by a couple of talented postdocs, Xiaoping Liu and Bifang Pan. And there was really a remarkable convergence of ideas and techniques and expertise that led to the successful outcome here. First was that Ping and I devised a chemical genetic strategy to interrogate specific TMC1 amino acids. We decided to generate genetic substitutions, swapping native amino acids in TMC1 for cysteine residues, and then use chemical compounds to selectively bind and inhibit those cysteine residues. And I really have to go back early in my career, credit Peter Gillespie for introducing me to the power of chemical genetics. So the second thing that was fortuitous was that we realized rather than making a mouse for each manipulation, we realized that we had these double knockout mice that had a null background and that we could use viral vectors to introduce TMCs that carried these cysteine substitutions. And then the third thing that seemed to work out quite well was that we realized that by injecting just a single microliter of vector into the inner ears of mice, we could express the mutant TMCs in thousands of double knockout hair cells, both vestibular hair cells and auditory hair cells. And we would dissect out the inner ears from these injected mice. Ping would take the vestibular organs, and Bifang would take the cochleas. Together, they generated reams of data. And so I just found it remarkable that with two different investigators working on two different physiology setups, two different organ systems, they kept coming back with the same answers. And it really boosted our confidence that we were on the right track. So let me just take a couple minutes to walk you through some of the key observations from this study. So we generated 17 different mutations, and they were in transmembrane domains 4, 5, 6, and 7. These were based on known deafness mutations that cause deafness in humans, as well as adjacent amino acid sites. We targeted a couple of negatively charged residues that you can see right here, as well as some that were based on a homology model that was generated based on TMEM16A, and then one negative control. And so the experiment was then we packaged those in viral vectors, transfected the hair cells, and then recorded from individual hair cells, applying these chemical reagents, MTSET, while stimulating hair bundles, recording the response. And so the chemistry was such that the cysteines have a sulfur side chain, and that was available to react with MTSET, forming a disulfide bond, linking this bulky side group. And so it's easy to imagine if you've got this bulky side group now sticking here in the middle of an ion channel pore, that it would inhibit the passage of current. And so this is what the data looked like. We would puff on the drug and give a repeating series of hair bundle deflections. And the data that emerged were just lovely. Nice transduction currents, and then as soon as the drug washed on, the currents were inhibited and could not be recovered. This was a very robust and repeatable response. And when we did it in control conditions, this is a mouse carrying the genetic mutation, but in the absence of the chemical inhibitor, there was no response. And in a wild type mouse with the inhibitor, there was no response. So it really depended on the intersection of the genetic mutation together with the chemical inhibition. And we did that for all 17 different mutations and found 5 that caused a reduction in current amplitude. We also looked at the calcium permeability and calcium selectivity and found that there was a reduction of calcium entry at 11 sites. So together, 5 sites with reduced current, 11 sites with reduced calcium permeability, 13 sites in total that had altered permeation properties. And so we went back to the topology model of TMC1 and mapped these 13 residues there. And we also realized that there was a homology with a known family of channels, anoctamines, that are part of a broader family, including TMEM16. This was a somewhat obscure paper published in 2009 from Han et al., but 3 different groups, Xiaoping Liu and I, David Corey and Nuranisa Akayuz, and then Angela Ballesteros and Kenton Schwartz realized that there was homology between the TMCs and the structure of TMEM16A. And so we could map the mutant sites that we had studied onto this homology model and found that they were right here within transmembrane domain 4, 5, 6, and 7. And if I put this in motion, you can see where the pore region of the channel is. So we felt like this was pretty definitive evidence at this point. And, you know, I think the data now are quite strong supporting the hypothesis that TMCs 1 and 2 are forming the hair cell transduction channel. I don't think that this is the end of the story. There's still probably more pieces to this puzzle, and I can't wait to see what other components of this transduction complex there are. Of course, we'd still love to see precisely how these molecules fit together and understand more about the structure of these molecules. And then once we've got that, understand how the transduction channel gates going from a closed state to an open state to enable the sense of hearing. So stay tuned for that. And I'll just wrap up now. I'd like to thank all of our collaborators. These are our co-authors on the TMC1 papers that we've published with together over the year. I wish I could have time to go into all of their contributions, but coming back to what I said at the beginning, I really feel like collaboration is one of the hallmarks of successful science. And this has been one of my greatest joys of being able to work on this project, is having so many wonderful collaborators. And in a final slide, I just want to give a shout out to my kids, Brandon and Megan. This is what Gwen and I collaborate on at home. And they've been incredibly supportive and patient and put up with 10 years of dinner table conversations about TMCs. So I'll stop there.
Wow, thank you for that incredible trifecta. Jeff, Gwen, and Andy, beautiful presentations and amazing research and collaborations. And we raise a glass to you and we applaud your beautiful research. And what a perfect selection for the inaugural award in this category. So thank you. And I'm going to now share my screen to now introduce our next inaugural award for this year is the Innovator Award in Clinical Sciences. And this is given to Charlie Della Santina, who is an MD and PhD, for the development of an implantable vestibular prosthesis capable of restoring balance function in humans. Charlie, it is so wonderful to see you get this award. This is what your certificate will look like when you receive it. And Paul is now going to introduce you and talk about you for a few minutes before we hand the Zoom screen on to you to tell us about your research. Congratulations, Charlie. It's absolutely such a fantastic selection, and I'm really looking forward to your presentation.
Hello, everyone. I'm Paul Fuchs, and it's my privilege today to introduce the inaugural recipient of the Clinical Innovator Award, Dr. Charlie Della Santina. This nomination was a joint effort with Ruth Ann Eatock and John Carey. So Charlie received his undergraduate degree in electrical engineering from UC Davis, and then went on to complete his MD and PhD in a combined program at UC San Francisco and UC Berkeley. His early training was a perfect predictor of today's outcome. His stated areas of interest at the time were signal and control theory, silicon micromachining, auditory neurophysiology. With that flying start, Charlie entered residency in otolaryngology, head and neck surgery at Johns Hopkins. And upon completion, he joined the Hopkins faculty, where he's now professor of otolaryngology, head and neck surgery, and professor of biomedical engineering. In addition to his research, clinical and surgical efforts, Charlie's director of the Cochlear Implant Center that provides care to more than 2,000 adults and children each year. Finally, he is founder, CEO, and CSO of Labyrinth Devices, LLC. I'd like to read a bit from the letter of nomination, which was composed jointly with Ruth Ann Eatock. Simply put, Charlie is the very definition of clinical innovator. His development of the multi-channel vestibular implant is a remarkable combination of basic, clinical, and engineering research, from initial concept to instrument design to preclinical animal experiments and now clinical application. Still more impressive, Charlie was the principal investigator for all of these stages, reflecting his training as an engineer, neurophysiologist, clinician, and surgeon. And from John Carey's letter, I'd like to read a little bit. John says, Charlie has labored through tremendous experimental and bureaucratic adversities, and he's overcome these challenges and advanced his design for the multi-channel vestibular implant to its first in human clinical trial for navigation in the real world. The team implanted the 9th participant just last month, and the preliminary results of this work are very exciting. Charlie's team has demonstrated that the implant can generate spatially appropriate eye movements in response to spontaneous head movements during natural behavior. And perhaps most importantly, patients report improved ability to walk and demonstrate objective improvements in postural gait and control. Postural control and gait, excuse me. There's much more that could be said about the remarkable story of the vestibular implant, but it remains only for me to say congratulations and to express admiration for this signal achievement in clinical innovation. Heartfelt congratulations to Charlie.
Thank you so much, Paul. That was beautiful.
Well, thank you. Is the audio okay?
Yeah, sounds great.
Fantastic. Paul, thank you very much for that very kind introduction, and thank you to all of you in the ARO for this award. What a tremendous honor to be given this award when there are so many more deserving people in our society. I hope that I can give you a sense of where this work has been, where it is now, and where it's headed. And throughout, I'll try to make it clear that I'm really representing the contributions of many, many people at many stages of the work. Many of them you see listed on the screen now, but I'll try to mention them as we go. I should disclose, as Paul mentioned, that I have an interest in Labyrinth Devices, which makes the equipment that we use, as well as parts of the implant. And right up front, I'd like to make the point that although our lab is actually a small lab, we only have 4 graduate students in the lab. We've had people now contributing over the past 2 decades to this project. And although I don't have time to go over each of them, each has made an important contribution. All the data that I'll show today that really involve our clinical trial work were acquired by the folks that you see on the screen here, and I'll try to make it clear as we go along. And the equipment that we use, the software that we rely upon, was created by those you see on the screen. I'd like to especially note Mehdi Rahman, Nick Valentine, and Nathan Vidowitz, all graduates of our lab who went on to work with Labyrinth Devices, as well as our large team that continues to grow of colleagues at MED-EL and support from NIDCD throughout this time. Well, for those of you who are not familiar with vestibular implant, I'm sure you all know about cochlear implants, and I just want to make sure we're on the same page. Why isn't there already a vestibular implant? We've been doing cochlear implants for decades now. The reason to develop a vestibular implant is because it's a disabling problem, not having vestibular function. You get oscillopsia, which is shaking vision whenever your head moves. You have difficulty walking, particularly on a kind of an uneven surface or in dim light. Brian Ward, formerly a trainee in the lab, now on our faculty, put together a nice epidemiologic study based on the National Health Interview Survey done in the US, which came to the conclusion that this is a disabling condition. Some 30% of people with this have stopped driving, 40% miss a lot of work, 60% avoid social activities. It's embarrassing to be thought of as drunk when you're leaving a party at night, holding onto your spouse's arm and being driven home, but that's the experience every time you go to a party when you don't have working vestibular function. These folks have a 24-fold increased risk of falling, and falls can lead to injuries that are very morbid. It's a pretty common problem. We estimate about a million folks in the world with severe loss. If you were to look at slightly less severe loss, it's getting up to about 1.8 or 2 million adults in the world. And so it's quite a large population that we're trying to help. And unfortunately, as a clinician, I have nothing to offer these patients other than telling them to get off of medicines that might make it worse and to do vestibular rehab and wait and hope that it gets better. And that's all the more striking because the year before I was born, Cohen, Suzuki, and others had already shown that you could fix this problem. Working in rhesus monkeys and in cats, in basic research labs that had translational impact decades later, they showed that you could selectively electrically stimulate the nerve branches going to the anterior, lateral, or posterior semicircular canals and get the appropriate constellation of eye muscle activity and eye movement that would move the eyes in 3 dimensions to compensate for the perceived head rotation. And thanks to the development of cochlear implants, almost all the technology needed to make a vestibular implant already existed as of about 2000. All you need to do really is get a motion sensor like what's now in all of your phones and add some electrodes into the canals and maybe later into the utricle and saccule. Now, to my knowledge, the first real effort to make a self-contained device that would do this was led by Daniel Merfeld, and he and Wangsong Gong, later also with Rick Lewis, made a single channel device. They mounted on a guinea pig's head and showed that they could stimulate the vestibular nerve. That later, I think, inspired work by Jean-Philippe Guillot, Conrad Wall, and then a growing group at Geneva, Maastricht University, to stimulate human subjects with vestibular loss, and a group in Seattle, Jim Phillips, Jay Broomstein, and others started up similar projects, while we at Johns Hopkins, inspired, I think, really by the work by Dan Merfeld, started working in chinchillas around 20 years ago and slowly worked our way to where we are now. Well, I'll argue that the benefits of doing a vestibular implant probably are going to end up outweighing the risks and costs. I would encourage anyone thinking about translational research to do an initial analysis of what's going to cost to implement their planned solution, because if it won't be cost effective, it probably won't be done in clinical practice. Dan Sun led that work in our group, and he compared cochlear implantation for adults, costs about $20,000 per quality adjusted life year, to knee replacement, about $70,000, to what we prospectively assumed vestibular implant might achieve. And we found that if we could just get 50% of the way back up to the quality of life reported by people who have one good labyrinth and one dead labyrinth, we'd be cost effective. And we've been working at it ever since. I'll just argue that one more reason to study this problem and to work on it is that if we have a way to fix vestibular loss, then it will drive interest in looking into why it happens in the first place. I'll note that if you Google sensorineural hearing loss, you get over 500,000 results. But if you Google sensorineural vestibular loss, you only get 5. And if you look for hereditary hearing loss, you get a carefully curated list of dozens and dozens of genes that also may have vestibular loss as their phenotype. But that's really just not been the focus of work. If you look up hereditary vestibular loss, you only get a couple of results. So I'm hopeful that with time, if we're able to do something about it, clinicians will work harder at diagnosing this problem, and then our colleagues throughout the field will have more of a reason to help identify the problem, characterize why it happens, how we can avoid it, and what to do when it does. Well, what we're trying to do to treat it now is to work with this model of a vestibular implant. Here you see in the lower right of your screen, the Labyrinth Devices MVI, multi-channel vestibular implant, is really just a modified Med-El cochlear implant, where the electrode array that normally would have gone to the cochlea is replaced by 3 sub-arrays, each with 3 electrode contacts to insert into the anterior canal, horizontal canal, and posterior canal ampullae. This other electrode here is just a reference electrode, not a cochlear implant. And we typically have been inserting it into the common crus of the labyrinth to try to steer current away from the facial nerve and cochlear nerve. But more recently, we've been putting it outside of the inner ear. There are a couple of extra magnets on this device to make sure that the head-worn unit, which contains the motion sensor that we use to measure head motion, will stay on the head and in the correct orientation, so the person doesn't get an abnormal percept of head rotation in the wrong axis. Or we were worried that when you have the device fall off, somebody would have a horrible vertigo attack and fall down. There's a power and control unit, which in our current version is worn on a lanyard around the neck. You can see here with our first subject, first participant. And then we use this head-on body rotating device and 3D goggles to track outcomes. The implant surgery approach is schematized here, and you can see we have 3 electrodes per ampulla, but we really only use 1 per canal. And my hope is that in the future, if we can optimize where that 1 electrode per canal should be, we will be able to spare extra electrodes to put onto a cochlear array so that we would have a combined cochlear vestibular implant, which is what has been the focus of the work in Europe and also in Seattle. Basic idea here is that the motion sensor senses head velocity in 3 dimensions. It's mapped through a static mapping from head velocity, either pulse rate or pulse amplitude or both. And then that pattern of pulses is delivered through the electrodes to each of the 3 branches going to the semicircular canals. Our current clinical model doesn't deliberately stimulate the utricle or saccule, although our animal work is focused on now developing that. Because time is short, I can't take you through the 20 years of work that got to this point, but I'll net it out to say that we started on animal work, just basic physiology of recording single unit responses in chinchillas and looking at their response after gentamicin ototoxicity about 20 years ago. About 8 to 10 years ago, we made a transition to replicating that work in rhesus monkeys, having shown that we could restore the vestibular ocular reflex in rodents. And then starting about 10 years ago, we started to work in earnest toward a first-in-human trial, which finally started about 5 years ago. So it can be a long haul. Our first implant surgery is now 4.5 years ago, 2016, and our first participant just came back to be retested a couple of weeks ago. Most recently was in this fall. And you can see that most of our patients have had ototoxic injury. I'll show you just briefly what this surgery looks like. This is in the second patient. For orientation, this is a left mastoid cavity. So we're looking behind the ear. In front of us here would be where the ear canal is. This is the posterior bony wall of the ear canal. Up to the right of your screen would be where the brain is above the mastoid cavity. And then down in the lower right of your screen is where a silicone template for the stimulator has been put inside of a bony well that will be under the skin. Well, we might open up the facial recess to prepare for a cochlear implant in the future if needed, identify the horizontal canal, and then find the anterior canal, also called the superior canal. Find the posterior canal, and then start making openings. Here you can see is an opening into the anterior canal and starting to make one into the horizontal canal. There's already one down here in the posterior canal right here. And then bring in the electrode array, insert it after a lot of fiddling, and then put in this case, a reference electrode in the common cruce, and then pack everything with some bone chips and other materials. Here's a nice CT reconstruction put together by Abder Hedjuj in our group, showing 3 electrode contacts in the anterior canal ampulla, 3 here in the horizontal canal ampulla, 3 in the posterior canal, and then here's a reference electrode, not really quite into the common cruce. Here in a 3D reconstruction Abder put together, you can see where these things are in relation to the lumen of the inner ear. Well, the first question, and really what I thought was going to be the dominant question for our work, is can a vestibular implant drive the eye stabilizing reflexes, the vestibulo-ocular reflex? For that work, I would point you, if you're interested in great detail, to this JCI Insight article from about 1.5 years ago now. The upshot is that all of our patients have an electrically evoked, 3-dimensionally appropriate vestibulo-ocular reflex, 3D VOR, for at least one electrode in each of the 3 implanted canals. Those responses pretty much align with the anatomic axis of the semicircular canal, as you could have guessed from Cohen and Suzuki's work in 1964. We can simultaneously stimulate pairs or all 3 canals to encode any intermediate access, again, something that we knew in the 1960s based on Cohen and Suzuki's work. And these responses in humans are actually quite large compared to some of the previous work that we'd seen in humans, but they're still kind of small compared to some of what we see in our non-human primate animal models. So I take that as a hopeful sign that if we continue to work at it, we'll be able to find a way to get even better responses. And the vestibulo-ocular reflex, either to whole body rotation in a chair in darkness or head-on body rotation with this motion modulated stimulation, exceeds our placebo control stimulation response of just constant pulsing rate with no motion information in every subject for every canal. To give you a sense of what this looks like, I'm going to show you generally responses that are around the horizontal VOR axis, it's really an earth vertical axis for rotations like this, or the left anterior, right posterior LARP axis for a head rotation around this axis, or for the right anterior, left posterior axis, which would be a turn around like this. And those colors, red, green, and blue, are going to be represented in all of these data. You can see that as we turn up the current, we get really quite big eye movements. These would be enough to stabilize your eye movements when you're jogging on a track. And they align pretty well with the horizontal canal, or here with the posterior canal, or with the anterior canal. When you map them out in 3 dimensions against the anatomic axes of the canals, you can see that even on the first day, we're getting pretty well aligned results. I think it's easier if you're not looking at vector diagrams all the time to just see how this goes. So if you reach up and you slightly wiggle the head-worn unit sensor in pitch, you can see, even in broad daylight, that we can drive someone's eye movement reflexes in the appropriate direction. So given the fact that usually vision would suppress the VOR in a brightly lit room like this, we're getting a pretty robust stimulus and response. Now, these responses can grow quite large as the current is turned up, but they're not huge in everybody. And so we have room to improve. And as I said, they're pretty well aligned with the canal axes, but not always in everyone. For instance, if you look here in subject 4, when we were trying to stimulate just the horizontal canal, and we would have expected to see an eye movement just around the axis of the horizontal canal, what we instead see is that both the left and the right eye are really turning about an axis. It's kind of a vector summation of what we would expect for the horizontal canal and for the nearby anterior canal. It's only a couple of 100 microns away, so it's not surprising that we're spreading current over to that branch of the vestibular nerve and getting an eye movement and probably a percept that instead of turning the head side to side, she feels like she's turning more about some other axis between these two. So we have room to improve there, although we found in animals, and to a lesser degree in people, that these responses align over time with practice and experience. Now, we can use that same vector summation approach to, for instance, deliver stimulation in antiphase between the posterior canal and the anterior canal on one side to encode a purely pitch head movement or to encode a roll head movement around your nasoccipital axis. So we have pretty good spatial control. Now, one thing that until very recently we hadn't had great success in is getting good vestibular ocular reflex responses to quick head rotations. This is critical for controlling the eyes in a way that keeps you from having oscillopsia, the shaking of the visual field whenever your head moves quickly. So the typical test we do for this is to move the head really quickly. Here is a quick head movement to the side like this. Blue is the head velocity, and in an ideal normal response, the eye movements in black would just follow that head velocity perfectly. But instead, preoperatively, you can see subject 2 has a delay and kind of a modest response, realizes that he's off target, and then jumps his eyes on target with the saccade. This is what makes it hard for him to see when driving because his eyes aren't on target most of the time. Now, after implantation, I implanted him in the left ear. We actually got worse because the stimulator's not on yet, and putting the electrode in probably bangs up the normal structures that he was relying on. When we turn on the stimulation, you can see that we actually are significantly better than without the stimulation and a little bit better than pre-op, but not all the way back to normal, that's for sure. That sort of pattern was true, and for instance, here's subject 3, post-operatively, a suppressed response, and then quite a good response, clearly better than where she was before, but not all the way back to normal. Subject 4, again, suppressed response because of mechanical trauma, and then up to, well, maybe a little bit better than before, but not huge. Well, we've just recently started thinking about why we're not getting better responses. And if you look at the latency of the response, it's not just a matter that the response isn't big enough, it's also that it starts too late. And why is that? Well, we realized, much too late, I think, that we really shouldn't be using just a static mapping of head velocity to pulse rate, but instead we should be using the acceleration of the head rotation as well. That's what the natural system does. And I had sort of made the mistake of relying on high pass dynamics of the rest of the nervous system to take care of that. We've just recently now started adding in this acceleration boost signal. And we had a great result recently in our 9th subject. You can see here, preoperatively, a really poor response. Postoperatively, still a poor response. With our usual velocity mapping, an okay response. But then once we kicked in this acceleration boost, it's remarkable. He's jumped all the way up to normal. And so we're very excited to do this. In fact, our 5th subject is going to be tested with the same routine tomorrow. So can we restore the vestibular-ocular reflex? Yeah, we can, at least part way. And these responses work for every canal and every patient. They align with the axis of the canal, and we can do them in combination. We weren't getting fantastic results for quick head movements until recently, but I think with this acceleration boost, we're going to. What about posture and gait? Well, for that, I would direct your attention to all of our data for the trial for the past 5 years, which have been bundled into this paper that just was published about 10 days ago in the New England Journal of Medicine. And I'll show you data on posture, gait, quality of life, and hearing. So now after more than 4.5 years to about 4 months continuous use, we see that all of our subjects report better walking and greater independence. All who used to rely on a family member to travel together come independently to their visits now. We found that 4 of our 5 clinical metrics of posture and gait are better than they were pre-op. The only one that isn't is gait speed, which was pretty much normal pre-op anyway. These are always better for the group than the constant rate stimulation placebo control condition that doesn't give any motion input. But some patients still have trouble standing with their eyes closed on a foam pad, and things like obesity or arthritis definitely are interfering with some of our results on these tests. I won't take you through this in great detail, but I'll just point out, if we look at this first panel, this is the Brunics-Ozoretsky test, which is a kind of a comprehensive test of balance postural tasks. It's really made for kids, but we've used it for our adult patients. And what we see here is at 6 months post-op and at 1 year post-op, in green are the within participant changes from preoperative baseline for each of our 8 subjects who have been followed for at least a year. You can see that overall, the median improvement has been not just statistically significant for this group, but also greater than the minimally important difference for this test. And those results hold up at a year post-op as well. Now, you can see here in black our placebo control condition, where we're just providing constant rate stimulation with no motion input. And you can see that that benefit goes away and people just appear to return back to where they were preoperatively. And that pattern is replicated with the modified Romberg test, which is standing eyes closed on foam, or with gait tests, including the dynamic gait index and the timed up and go. The one place where we don't see much of a change is gait speed, but that's because most of our patients, almost all of them, had roughly normal gait speed early on. Here's what a modified Romberg looks like preoperatively. You can see this is our first participant. He was a marathon runner until losing his vestibular function to gentamicin ototoxicity, and just isn't able to do that task, whereas about well, within a few months after onset, but here at 11 months out, he's able to stand with his, with his eyes closed throughout. Here you can see what looks like a pretty normal gait until you see him try to round a corner and he has to slow down and wobble a bit. And you can see that if you ask him just to look left and right, he kind of veers off target, even in a well-lit room. Now, he sent us a series of videos as he returned to jogging on a treadmill in the gym, which was amazing 4 months out, and then took up jumping rope and came out to Baltimore to go jog around the Inner Harbor with the study team. So really just an amazing result in that case, and our other patients have had similar improvements. Now, what about quality of life metrics? Well, we do several. For measuring patient-reported dizziness, we use the Dizziness Handicap Inventory. A severe deficit or handicap would be in this gray zone. We want these numbers to come down. And for the group, they've certainly come down over time for everyone, although we have still one patient who's reporting moderate dizziness. We use the Vestibular Activities of Daily Living scale, which is another metric of how vestibular loss impacts you. And you can see that everyone has improved on that scale as well. This big transition is going from needing a cane to not needing a cane anymore. On general health-related quality of life metrics, we see that the SF-36 utility score has improved overall for the group. The Health Utility Index Mark III really heavily weights hearing, and in part because some of our patients have had hearing loss, those results have not been statistically significantly improved. They've sort of bounced around 0, slightly positive. Now, in real life, quality of life means something like this. It means jogging at the gym or being able to do household chores without asking for help, tending to your farm or your garden, riding a bike, walking on the beach or walking in snow or dancing at your daughter's wedding. And all of our subjects are doing things like this that they couldn't do before. Now, what about hearing? Well, hearing is potentially normal in the ear preoperatively. That's unique to this trial. So far, the other work done in Geneva, Maastricht, Seattle has involved doing a cochlear implant in a patient who has profound hearing loss. And so we don't know that much from those trials yet about the impact on hearing if you were to put a vestibular implant in a person with normal hearing pre-op. But what we found so far is that 5 of our 9 subjects have had preservation of hearing that's useful to carry on a phone conversation without a hearing aid. It's not clear to me why hearing is better in some than in others. So far, all of our subjects say that they're content with their trade-off, but of course, we want to do all we can as a field to sort out what determines who will have good hearing preservation and who won't, so that we can adapt our surgical strategies, our pharmacologic interventions to make sure that we have hearing results that are as consistently good after vestibular implantation as our vestibular preservation results are consistently good after cochlear implantation. Overall, interestingly, 3 of our 9 patients have had transiently improved bone conduction sound. early after surgery. That's what we see in spirit canal dehiscence when there's an opening, a third mobile window into the labyrinth. And I suspect that it may be that because I'm making a third, a fourth, a fifth, and sometimes a sixth opening into the labyrinth, we may be intraoperatively causing bony hyperacusis, which could then lead to at least the high frequency sensorineural hearing loss that we've seen really in all of our patients have had some degree of what looks like it might be a noise-induced hearing loss, but it's unclear. We always can elicit tinnitus if we turn the current up high enough. That's not surprising, but we can find an effective current for vestibular stimulation without causing tinnitus for every canal in every subject. Well, it's hard to balance, hearing loss in 1 year for the patients, 3 of 8 who've had profound hearing loss or severe hearing loss when followed out 6 months or longer. It's hard to balance that off against gaining vestibular function. I thought it would be best if you could hear from at least one patient's experience. So I'd like to share an interview after going over these data. Here you can see, these are all data in the New England Journal of Medicine paper showing pre-op, 3 weeks post-op, 6 months and 1 year post-op audiograms for everyone. What you can see really is that our hearing results break into a bimodal distribution where 5 of the 8 patients who have been followed out for a year have quite good hearing, and 3 of those 8 don't. So our job is really to figure out how to move those 3 up into the group of the rest in the future. Well, here's that interview I mentioned, and I'll just be quiet. I'd like you to hear her thoughts on her oscillopsia, shaky vision, and other symptoms.
What's your status now in terms of your oscillopsia?
Very, very mild. It's still there, but nothing compared to it's very, very slow now. Where before, most of the time it was a very fast. Now it's very slow. I can read street signs. I could not read the green street sign before, and I can now when I'm riding in a car.
Okay.
And I could not do that.
Are you driving? Maybe I shouldn't ask. And what's your walking like now?
Much different. It's not perfect. I never thought it would be, but compared to before, it's night and day. I actually relax when I walk. I feel relaxed now when I walk. It's not a complete struggle just to take a step.
All right. Do you use a cane or a walking stick? Or?
No.
Okay. How's your work going?
Much better.
Right.
Much better.
Is there any effect in either direction on your work or your ability
it's
to
much
work?
better. My concentration alone, the fatigue, it's 1,000 times better. I mean, I had to struggle just to get through every day. And by the time I was finished at work, and I worked behind a desk, I was exhausted. There was nothing left.
How's your mood?
Much better.
Okay.
Much better. Everybody, it's funny because most people tell me now that I actually have a smile on my face. I didn't before.
Okay. That's good. Are you still doing rehab-like exercises?
Probably not as much as I should be, but a lot of times I'm so active now that I actually, to be honest, I forget to do them because I guess I forget that there's anything wrong now. I mean, for me, this is incredible.
What's your hearing situation?
It's bad.
Yeah, it's bad. I saw you in your hearing test, actually, it went down a little further. I'm sorry.
You know what? I knew, and for what I've gotten, I don't care.
Well, I'm glad to hear that. I care, and I'm sorry, and I'm still hoping it comes back up.
You know, sorry. I'm sorry, I don't care. I mean, you have no idea what I've gained. None.
Okay.
Just in how I feel about life now. So, it's completely different.
Great.
Sorry.
Knowing everything you know as of today, what would you advise, to have an implant or not, and why?
To do it in a minute. It changed my whole life. I mean, I went from barely functional to I could pretty much do whatever I want now. My biggest restraints now are heights. I still am very careful. I choose not to do that now, and the swimming because of the device. But other than that, I feel like I could do pretty much anything I wanted to.
So our overall status as of today, after nearly 4.5 years of continuous use for our first participant and about 4 months for our most recent, all of our subjects use their system either 24 hours a day or they take it off like they take their glasses off when they go to bed at night. All requested long-term use, and the FDA approved that for all of them, all have a prosthetically evoked vestibular ocular reflex for each of their 3 canals, which aligns approximately with the canal we're targeting. And it looks like the acceleration boost has a great chance of improving performance further. 5 have useful implant side hearing. 3, including the person you just heard interviewed, don't. And then 1's recently implanted, had a hearing drop, but it's been improving since, so he's evolving. We have median improvements in the within participant change in metrics of posture, gait, disability, and quality of life. All of our patients report in their daily lives greater independence. And the FDA just this fall reviewed our data and approved an expansion of the trial now to 30 subjects. So I think the future is bright. I'll just leave you with 2 things about what we're heading toward. One question is, well, in cochlear implantation, we worry about implanting people who lost their hearing a long time ago because we worry that you'll have sort of central synaptic pruning and we just won't get a great hearing result. In our 8th study participant, he had lost his function as a graduate student studying for his PhD in his 20s, 24 years ago. And was implanted now just last year. You can see
Ready?
Yep.
All right. I'm going to wiggle your device in pitch.
Wow.
Oh, Lord.
So you can see that he has vibrant response.
And in yaw.
In 2 decades, well, 2.5 decades after the onset of loss.
And in pitch.
For
and in yaw.
For a vestibular implant now all this time. And then mostly I've talked to you about people who have ototoxic injury. So we know the injury is in the hair cells, but more than half of patients with vestibular loss have idiopathic loss. And although I suspect many of them have a genetic defect that affects hair cells, and I really hope that my colleagues who are just presenting will turn their attentions toward the vestibular aspects of hair cells in the future, even more than they already have. We need to figure out what's going on in patients who have still idiopathic loss. Can this vestibular implant work for them? Or is it more common that the lesion is downstream of the inner ear? So far, in the 2 cases that we've done, we can get a great result there as well. So I think the future is bright for this as a clinical treatment to get through the rest of the path. With that, I know my time is coming to an end, and there are too many people to thank in the time that I've left available to me. So in addition to thanking the ARO, and then in particular to Paul Fuchs and Ruth Ann Etok and John Carey, who nominated me, and to others on the ARO Council who granted this award, I'd like to thank the pioneers. Really, the first now 9 participants in this trial are true pioneers and partners in this work. There are 3 of them, our first, 3rd, and 4th participants in the trial with some of the study team on a picnic day in Baltimore. Just amazing people. And think about what they're doing. Maybe not putting your life at risk quite the same as being an astronaut, but pretty darn close. So just pioneers in our field. And I'd like to just briefly, if you'd indulge me, say some thanks to people who I haven't mentioned in talking about this work. Because although they weren't directly involved in this work now, their guidance, mentorship, and partnership has been formative for me in getting to this point. Ted Lewis, one of the founding members of the ARO, Greg Kovacs, Mike Merznick are three of the most important men who put me on my path toward doing this type of work at UC Berkeley, at Stanford, and UCSF. Since having the fortune to arrive at Johns Hopkins, I met Lloyd Miner, who I'm sure everyone in ARO knows. And I was lucky to be one of the cohort of people that he brought into the lab and mentored just expertly. I strive to follow that example every day as I try to mentor students in my lab. David Z, John DeParco have also brought critically important mentorship into my life. And although John, Carrie, and I are about the same age, I think he's a month older. I have to tell you that he's like having that overperforming, slightly older twin who sets a standard that helps you drive to do better. Just an amazing colleague and friend to have, and a great collaborator to have. And so many other collaborators. Early in this work, America Muliacho, Gene Friedman, Chenkai Dai, Tim Huller made formative input to what now is a vestibular implant. And Kathy Cullen, Xiaoqing Wang, Michael Schubert, Mohammed Lahar, Steve Bowditch, and others who I can't have time to mention right now have made critical contributions along the way, as well as everyone that you see on the screen here as well. So with that, I know my time is at an end. I'll say thank you to all of you.
Wow, thank you so much, Charlie. I think we're all applauding you virtually, and this is absolutely beautiful, beautiful talk and such important work. And I look forward to continuing to see the progress. This concludes our annual award ceremony. I want to thank everyone again for being here to learn from our award recipients and to celebrate the incredible work of colleagues and friends of ARO. I hope that everyone enjoys the rest of the day and the meeting. I wish you all health, safety, and hoping for a return to more normal in the future. So have a great day, and congratulations again to all of these fabulous award winners.